Okay, hello everyone. For those of you who are here and also for those of you who have joined us online, welcome to the final presentation of Master of Architecture in Emerging Technologies and Design here at the AA. This concludes the 16-month journey of our MArch students who started back in September 2024. This year, for those of you who are joining online, just give a brief overview of what our studio were up to. We and our students have tackled and investigated a range of global architectural, urban, and environmental issues, from inhabiting the desert landscape in Egypt to bioremediating the abandoned mine sites in India, proposing architectural interventions to tackle the mucilage issue in Istanbul, Turkey, coming up with novel solutions to grow sandbars in order to preserve productive lagoons in Taiwan, and finally working and building with dynamics of riverbeds in India. All of them are quite diverse in solutions they proposed and the issues they tackled. And we, faculty, were very excited to see how these projects have been concluded. I am Mila Shokatbakhsh, the program director of EmTech, and I'm here with our esteemed faculty and our guest jury members in the lecture hall. We have Mattia Santi with us, co-founder and director of Sassi Studio, award-winning design and architecture firm here in London, and part of the AA Media Studies team. Pablo Zamorano, head of geometry and computational design team at Heatherwick, also the lead AI strategist in the same studio. Nacho Marti, the co-head of environmental and technical studies here at the AA and the director of a very interesting business school called Amazon. And Jonah Gonsalves, the associate professor at Bartlett, part of the ETS team, and author of a very interesting book. That's actually how I know you, the environmental performance of tall buildings, expert in environmental design. Without further ado, I would like to invite our first group, Subterranean Currents, here to the podium. The floor is yours. Thank you.
Hello, everyone, and thank you for being here. We are delighted to share with you our dissertation, Subterranean Currents. Our research started by asking how arid landscapes can be sustainably inhabited. These landscapes already comprise a significant portion of the Earth's surface and are projected to expand further. And interestingly, these territories often coincide with transboundary fossil aquifers that remain largely untapped. We focus on the Nubian Sandstone Aquifer, which spans 4 countries, and it has sustained life in multiple oases for centuries. On it, Egypt presents a stark contrast: dense settlements along the Nile and vast uninhabited deserts. Its overdependence on the river and rapid population growth create an increasingly unstable condition. Within Egypt's desert, the Bahariya oasis stands out for its strategic location along the government's planned desert expansion corridor. The economy of the oasis relies primarily on agriculture, supported by underground wells, and sustains a population of 50,000 people. Current settlement patterns align closely with heavy reliance of the local population on water availability. Abandoned farmland and settlements highlight the growing pressure of water scarcity. Our research proposes a prototypical subterranean settlement that harnesses passive atmospheric condensation and groundwater to ease water scarcity and catalyze urban decentralization in hyper-arid regions. The project begins at the territorial scale, shaping economic patterns and sustainable water cycles. Then shifts to the urban scale, where social and environmental regulation are consolidated into a settlement proposal. We began by carving out an optimal landscape from within the Bahariya and mapped the aquifer's morphology beneath the oasis. Given limited data, we used a predictive model trained on magnetic sounding station points compiled from existing literature. We then overlaid the aquifer model with soil quality and settlement pattern analysis to pinpoint the most suitable site location for the settlement. And within this area, we also identified optimal well locations based on the aquifer's analysis. The settlement's organizational logic is structured around water production and consumption data, organizing the territory in 4 architectural unit typologies as shown in the infographic. A rule-based aggregation process combined water distribution networks and topographic analysis to generate the optimal settlement landscape. In parallel, material experiments using resources extracted from the oasis produce a functionally graded material that transitions from high thermal mass to water resistance, enabling strategic control of water circulation and heat absorption. Finally, an iterative reusable brick formwork produced an interlocking system that channels the material into high compression vaults.
Next, the 4 architectural units were developed individually to define the internal mechanisms, starting with exploring the concept of atmospheric water harvesting. Drawing on precedents such as just wind towers, we created a water harvesting tower that uses solar-heated air from its structure to sustain continuous upward airflow through the stack effect. The updraft creates a pressure differential that draws hot air underground and cools it, resulting in a large-scale condensation process that produces about 2,800 liters per day. Assembled, these structures forms a condensation farm. Cistern units are designed by merging communal spaces with water storage infrastructure. Drawing on bolted structural precedents, the design consolidates water storage and communal spaces into a unified roof system. Morphological experiments were undertaken to balance programmatic cohesion with improved environmental performance, resulting in a radial spatial arrangement around the water storage, aided by unified multi-level vault morphology. Residential clusters serve as the primary habitable spaces of the settlement. Informed by desert settlement patterns, each cluster comprises 5 residences organized into public and private quarters, surrounded by water bodies for evaporative cooling. Assemblies were explored to enhance environmental performance, increase compactness, and regulate public and private relations through visual control. The outcome was a central courtyard typology, where public spaces radiate from the core and private quarters line the perimeter. Additional private quarters occupy the ground level of this aggregation. Finally, agriculture is merged with water reuse practices into a single typology. The analysis of purification processes inform a unit that integrates wheat and palm plantations with papyrus-assisted purification pools supplied by water from nearby housing clusters. Studies on optimal water flows and plantation placement frame this experiment. This produced a submerged typology of visitable green and water spaces. All of these studies, including optimal and less optimal outcomes, are systematized in a catalog through which the urban scale can be selectively populated. And following this fragmentation process, what occurred was collapse. Indeed, the fragmentation process produced a series of heterogeneous mosaics. Discontinuities, overlaps, and mismatches emerged in an assembled condition and drove the research into a different direction. This clash catalog constituted an initial attempt to explore a fraction of the combinatory possibilities arising. Moving forward, the resolution of this spatial collapse was pursued through the process of even further collapse, an abstraction of the 4 units. When taken apart, a condensation farm resolves into a field of tower systems occupying a wider area to sustain the atmospheric processes. Water and pedestrian networks interlink these towers and may overlap. Cisterns can be understood as an overlay of subterranean and ground platforms, capped by an underground layer of bolted structures. Programmatically, they are segmented into water storage, communal, and public spaces. Water storage is confined to the subterranean realm, while communal and public spaces form 2-tier structures that are either enclosed or open through wooden lattice systems. Residential units are decomposed into subterranean private quarters combined with peripheral buffer zones and ground-level public quarters. When buffer zones come into contact with each other, an internal courtyard is formed, thus encoding its emergence within the abstraction process when combined with other typologies. The same buffer allows shaded alleys to emerge. Finally, agricultural units are segmented into plantations and purification systems, interconnected through the same pedestrian and water networks as the condensation towers. The elevation is encoded as a gradual increase the further they extended from adjacent build structures. All abstracted spaces are evaluated across 4 qualitative metrics: thermal, humidity, acoustic, and visibility. Assessing these spaces in isolation cannot produce reliable results, as spatial qualities are inherently relational and mutually influential. To address this, the research contextualizes qualitative assessment through a dual framework. Each space is assigned an intrinsic value, derived from its architectural and environmental properties, and also a transmissive value, which encodes the extent to which that space influences the condition of its surrounding environment. The evaluation of these spaces introduces an additional layer of abstraction, in which architectural elements are no longer defined solely by their volumetric characteristics, but also by qualitative identities directly tied to their function. In terms of environmental performance, water storages are inherently associated with high humidity levels, while towers generate excess heat and absorb moisture as the byproduct of the condensation processes. Combining privacy and visibility metrics allow us to regulate transitions from private to public life. Public spaces are inherently associated with elevated acoustic activity, while dense urban formations rapidly obstruct visibility and generate compact spatial patterns.
Encoding these functional and spatial footprints produces a new class catalog that operates simultaneously on spatial and performance dimensions. In this sense, it can be better understood as a matrix. This matrix is subsequently operationalized in the reassembly process of the settlement. As a testbed of a neighborhood comprising 16 architectural units and accommodating approximately 320 inhabitants is examined. The reassembly process begins by abstracting the original settlement into its constituent spatial elements and reorganizing them according to a set of spatial rules that define the underlying urban logic. The resulting aggregation is then architecturally articulated through an additional layer of spatial rule sets. The system operates across 3 layers, vertically segmenting the settlement into subterranean, ground, and overground strata and distributing the spaces according to their spatial expression. For example, a tower with a 25-meter vertical span necessarily occupies all strata, together with its surrounding buffer zone. Water and subterranean path networks interconnecting hydrological infrastructure create opportunities for their intersection to be exposed spatially as floating plinths. When cisterns intersect with other structures, opportunities arise for their vault systems to recede and expose water tanks within public spaces. Water networks, when combined with the residual public spaces shaped by private housing quarters, produce dense public ensembles with reduced solar exposure and intensified contact with water systems. The interconnection of public housing quarters through ground-level pathways and terrace systems generated by private quarters establish the public-facing domain of the settlement. Communal spaces can assume multiple internal configurations, which, when framed by rigid vault systems, allow for vertical interplay in their spatial expression. Public spaces allow for intersections with other settlement functions. Agricultural fields may occupy their subterranean layer and form internal gardens. When this occurs, the corresponding ground-level footprint is subtracted to resolve vertical conflicts. Overground paths project onto the subterranean realm through colonnade systems and generate shaded routes as an additional layer of spatial organization. Finally, agricultural fields are allowed to extend into all public subterranean spaces, gradually transforming into garden configurations. However, this constitutes only the spatial matrix organizing the settlement's typological patterns. The qualitative matrix is developed by assigning performance metrics to all configured spaces. Each space is attributed 4 quality metrics calculated as the sum of its intrinsic value and the average transmissive values of neighboring spatial volumes within a 15-meter radius. As the final component that activates the system, the 3 path networks of the settlement operate as its primary drivers. Each network is required to interconnect specific spatial typologies and to perform global calculations that consolidate all qualitative metrics into benchmarks, either as overall averages or as rates of qualitative change along the network. By calibrating these benchmarks, the reassembly process is transformed into a set of algebraic operations, a sort of algebraic synthesis.
The wealth of options that can be examined is as many as the benchmark combinations and the sizes of the assemblages. The following section examines 4 such assemblages. We could first start by conceiving the most thermally regulated settlement. We just have to lower the temperature metrics on the subterranean network and increase the humidity circulation along the settlement's water infrastructure. With a global average temperature of 28 degrees, we can observe that the naturally cooler and most humid areas of the settlement are distributed along its periphery, forming a sort of thermal barrier. Expanding on this system, architectural vernacular shading system known as mosharbayas envelops housing units and their internal courtyards. The residences themselves can now coexist with private gardens, where purification pools immediately turn grey as their supply, while also providing evaporative cooling. And ground path formations are transformed to shaded entrances that lead into their subterranean quarters. In this assemblage, productive landscapes and colonnade systems become the connective tissue of housing clusters. Another attempt will be to render the settlement as quiet as possible, lowering its global acoustic threshold while also maintaining stable visibility rates for a homogeneous spatial distribution. Acoustic and visual performance is shown to overlap in spaces, mainly dominated by agricultural fields framed by colonnade systems. The colonnade systems selectively shaded water surfaces and interconnect housing units. And in other times allows for parallel roads along water networks generated by condensation towers. In some cases, large colonnade systems completely segmented agricultural plots. We decided to amplify this condition by sealing them with mosharbaya covers, and typologically mimic the Egyptian garden.
Public spaces could become central pieces of a certain assemblage, overlooking the entire settlement through the increase of their visibility metrics and amplify their temperature differentials, enhancing a sense of environmental delight. This resulted in public spaces being enveloped by agricultural plots, expanding their field of vision and decreasing the temperature. Such spaces can be permeated by these plots and create shaded gardens that also host public markets on the ground level platforms, and through their intersection with terrace systems, they can expand their functions outwards. And these alterations can become the framework for the design articulation. Finally, we could even conceive an extremely humid settlement, where the rate of its atmospheric and water exchange are rapidly circulating. The resulting assemblage forms dense humidity corridors that merge water infrastructure into centralized systems. Taking advantage of exposed water storage tanks, we might create pools for recreational use with platform configurations. When purification systems and agricultural plots merge into greater assemblies, they can act as core humidity producers that the condensation towers can take advantage of. Finally, the humidity corridors ends by ascending to the ground level through artificial valleys produced by agricultural plot formations. Even the design of boundaries with water flows enables a concessionary dynamic between public spaces and water infrastructure. These four assemblages sit at an array of possibilities that move between qualities and scales, and we could even say that navigating the matrix between is a process of composition on its own. This thesis proposes a way to transform arid frontiers and moves between scales and datascapes, between options and interpretations. Before we conclude, we would like to highlight that this process, as transparently as we were able to show it, avoids a deterministic approach, not for a lack of decisiveness, but rather to highlight design as a domain of dialogue and concession, fitting to the transboundary nature of deserts and aquifers, a landscape that metabolizes subterranean currents. Thank you.
Thank you very much. Impressive work, very, very comprehensive, very bold. And I think my first question would be about the deployment of, or the growth, the sequencing of this. No? There seems to be some seed modules, some seed elements. So I would like to hear your thoughts about how do you think this grows over time. So is there a moment where you only use 4 of these units, and then after a certain time you continue to grow, or do you imagine that there is a minimum set of units that you need to apply in a specific context? In short, what are your thoughts about the timeline of these? What's the minimum you can use? What would be the maximum for a given site?
I think when conceiving the different elements of the settlement, we visualize the expansion programmatically. So we begin by constructing the cisterns, which are the water storage elements of the settlement, and these gradually expand to the public areas of the settlement and then the housing units of the settlement. And this kind of actually aids to the construction process, because building large vaulted structures perhaps can aid in the construction process. And it's a gradual process, I would say, of developing the public domain, the private domain, and then the agricultural plots, the productive landscape.
Yes.
Yeah, no, thanks for the presentation. It was really good. I'm also quite impressed about the amount of work you put together, and the quality of the work, I think, is quite impressive. My question, I suppose, it's more about your project from the side of the inhabitants. So it looks like the organizational system that you put together responds to, as you mentioned, some kind of hard data and also some qualitative data, including things like view corridors and stuff like that. I wonder really how this reflects the actual view from the inhabitants from the street level, or if there is some other type of kind of identifier that you're using to guide the organization of these settlements. At the moment, if I see this beautiful rendering that you have, let's say, in front of us, it feels like it would be a little bit hard to understand where you are, in a way, if you have to get to a different part of this district. Mm-hmm. You know, okay. What's driving that organization from the side of the inhabitant?
Well, we were thinking about this, and I think that the main driver as like a point of reference is the condensation towers. This is like the key feature that kind of would orient you around the settlement. And actually, the condensation towers themselves produce water networks. They call them canat systems. It's the vernacular way to call them. And actually, pedestrians could even orient themselves through the canat networks. So actually following the water paths becomes a way of navigating in the settlement. In terms of visual perception, at the subterranean level, it's something that we didn't explore. We explored the visual perception of the public spaces. But this can be very easily done just by calibrating the settlement according to the visibility metrics of the subterranean network.
Yeah.
Thanks.
Thank you.
Maybe I can jump in. Thank you for the presentation. Very, as was said already, very comprehensive, incredible amount of work. I'm really going to invite you for a coffee or a drink after that, because I have so much to talk to you about the project. It opens so many possibilities. And I'm sure you are in control of the various steps. But I have, it's more of a comment than a question, and I would like you to comment on that. It seems to me a quite complex analytical base to get to the various forms or urban design possibilities that you showed. But you often talk about optimization. We optimize to this, we optimize to that. But I saw very little data. We just saw the outcomes. So as we talk about optimization, I think maybe you can explain or clarify, use one example. Mm-hmm. Are you optimization towards what? What kind of variation from extreme conditions to more desirable conditions? In any way, it could be climate, it could be amount of water. Were you working with? How challenging it was? I think that's something that didn't come out very clearly in the presentation. How challenging it was to get to the conditions that you wanted, and I couldn't really understand what did you want to achieve in terms of, in the end of the day, quantity or quality. I'm sure it's there because it drove your analytical work, but you didn't mention. So that maybe if you can comment or give one example of a quantifiable condition.
Yeah, on the qualitative analysis that we develop, we measure all these qualities based on the first approach we did on the initial units. So these initial units also have a pre-analysis that we develop. So all the moisture bayas, the vaulted ceilings, all the architecture, the material we use is embedded inside all of these analyses. So in this way, we already knew the baseline to produce like this new organization. And we also relate between them. We do some mathematical work of algebraic, where we find the average of these qualities, and we also, based on the optimization, we can calibrate which one we prefer. So in this case, we were choosing 2 qualities per settlement to optimize them based on those 2.
It's important to consider, by the way, that this process is done in 2 parts. The first part, the unit analysis part, is conducted to extract typologies. For example, you asked about a specific instance, perhaps. When researching the cisterns, we calibrated them according to thermal performance, so self-shading, ventilation. If you notice, for example, the cisterns are oriented all at the same location. That is because they try to harness the prevailing winds and obstruct the dust winds that come from the others.
Yeah, perfect. You just hit on the point. This kind of conditions you're designing for, which are inputs, for example, wind direction, I think it's really important that you are clear about it, because that's where the whole discussion starts.
Yes.
But then, okay, so clear, thank you. And one last comment is, once you have that final result, for example, the image that we have there, and thinking of environmental principles, material principles, I think looking critically and say, okay, so this is, let's say, the optimized, or one of the options that you have in the end. How much more opportunities or possibilities does it open? Because, for example, the catchers, the towers, you do them to condensate water, but they are also great ventilators.
Yes.
And depending on the space that you want to ventilate, they can take different sizes. So all of a sudden, a field of towers which are optimized for one condition can still respond to that, but create variation and be more organic as a city is. Being more multi-criteria. So I think you got to a fantastic point, a great synthesis, but from that point onwards, what I think would be a great exercise to do is imagining, as you add multi-criteria, how variant this could become, and maybe less homogeneous. Not at the ground level, you have a lot of diversity, but then using the towers, for example, it can be a great urban element. Anyway, I stop here, but congratulations.
Thank you.
Thank you.
It's essentially bridging the two parts into one equal part, like transforming typologies into the urban landscape and expanding them and contracting them.
Congratulations on the great work you presented. I think it's very well documented and very comprehensive. You have been considering so many different aspects. I think it's a very contemporary project, tackling a lot of issues of sustainability. It's very interesting that you, you identified problems that are specific to the territory. I think it would be interesting at the end to understand how, and then your project is actually contributing to addressing some of the problems that are the beginning of your thesis. So it would be important, very important, to have a clear understanding how, at the end, your project, respond to the initial thesis that you are stating. But I think, there is a lot there that you're already talking about it. Also, it's very interesting to see, I'm very happy to see that you're working a lot with bolts, and you're working a lot with vernacular materials, the Mashariba patterns that you're talking about as a passive shading device. I think it's very important because you are bringing back, structural topologies that are actually taking in consideration how the material works. And this is an important thing, especially because your project is a lot about materials, about vernacular materials and traditional technologies. So I think from a passive point of view, it's very clear that you're using a lot of passive technologies to deliver sustainable solution. It would be interesting to understand if there are some active technologies that could be interesting for you to combine with the passive technologies you are widely using to, not only conserve or collect water, but also probably produce some energy on site, because there is a lot of potential to combine passive with active sustainable technologies to, probably further increase the performance of the overall development. Another important aspect, I think, this is a comment that comes from the images. Like, I see very uniform and earth colors, but it's also important when you talk about visibility. I think it would be interesting to express also parameter of orientation, not only visibility, so how wayfinding works. So having some element, like for example, nowadays we're used to see contemporary, old architecture, like for example, Greek temples, they're all white, but historically they're not all white. They had paintings, they had colors. So how these elements, for example, could be part of the project to help people orient themselves within development. And another thing that I find very interesting, I think is very, very exciting to see, all this translation to algebra, to these sort of matrices that you've been using to document each one of the building topologies. I think it's a very interesting thing, and you have a good point there. I think you should invest a little bit more on that and express, how this, algebraic approach has been helping you to drive this emergent design. So, how this algorithmic approach that you had there effectively translated in the design iteration to make the project more optimized. So I think this is an aspect that you have is already embedded in your project. Just express this a little bit more. So, yeah.
Just perhaps one more comment. It would be nice if you could reflect on how the system you're proposing reacts to non-linearity. At points, it seems that you know what's going to happen, and that allows you to predict the growth and evaluate. But it would be nice to reflect what happens if things don't go to plan. No, so you run out of water. You're not able to condensate water for certain reasons. So to understand how growth would be affected by this non-linearity. My perception by looking at the presentation is that everything was business as usual, no? So it would be nice to understand what happens if something goes wrong, no?
Yeah.
Do you decrease the growth? Do you stop? Do you abandon? Do you modify certain things? So I think that would be something interesting to wrap up the wonderful project.
Yes.
Thank you.
Thank you.
Hello everyone, my name is Jinkya and this is my teammate Louis, and our dissertation name is Post-Mining Palimpsest. For over a century, coal mining has been at the heart of the industrial growth and the energy production. From Europe's early factories to China's vast energy grids and America's steel towns, it has reshaped entire landscapes and the communities. Today, there are still close to 6,000 active mining sites. With the rising awareness of global warming and the massive carbon footprint of coal combustion, the industry is in decline. India is the second largest producer and the consumer of the coal. The Jharia coalfield is the nation's most important storehouse of that. It covers an area of 450 square kilometers, and nearly all the India's coking coal is sourced from here. Jharia's air is loaded with the toxic gases and dust. Vegetation here doesn't grow, it struggles. Dense forest cover is almost gone. The same fires that burn below also eat away the ground, causing subsidence of 20 to 40 centimeters per year. Entire settlements sit on the burning ground, where the houses crack and the sink as land subsidize. These abandoned mines hold the potential to become the ecological reservoirs if the heavy metals are neutralized and vegetation is reintroduced. So the question is, how can this abandoned landscape can be converted into productive system that can restore the environment? So these are the continuous chain of the mining zones operated by the Indian Mining Organization. These are the 11 major mining areas sit along this corridor, cutting through the existing settlements, transport lines, and the ecological systems. The selected site has the maximum ground subsidence. Deep mine voids and the underground fires are causing continuous land sinking. These are affecting more than 150,000 people. There's like 60% reduction in forest cover. The loss of forest directly translates to the loss of the stability of the people living here. And this purple gradient isn't just a poor air. It's the map of how the dust, fumes, and underground fires travel. More than 60% of people face health issues, and villages inside are hazardous zones. So the mine shaft covers approximately 900 to 400 meters with the depth of 80 meters, while the soils heap covers 400 into 400 meters with a height of 60 meters. So these dimensions underscore the scale and the magnitude of the intervention and need to generate the localized data for informed decision making. So this thesis frames soil remediation as the foundation for the regeneration by restoring degraded mining landscapes through ecological and planting strategies. Ground becomes productive once again. This environmental recovery enables social remediation, allowing architecture to re-emerge as a consequence of the healed land rather than as an imposed intervention.
In order to understand the soil regeneration process, we did a study of ecological remediation process, where we investigate concepts such as risk of filtration, fight extraction, risk of degradation, and others. The idea is that these mechanisms plants act as differentiated agents. Some isolate and immobilize heavy metals, others enhance nutrients in the soil, while others increase soil cohesion and stability. All the components of plants act in the progress of regeneration, in which pollutants are transformed and released as vapor through leaves. Understanding this process suggests that plants must be classified according to their functional role within the remediation process, forming the basis of the strategy that we developed. In this way, to address such a hostile and large terrain composed of multiple layers, the strategy was to extract detailed data from the intervention zone. So we divide the terrain into patches of 5 meters by 5 meters to apply data to each unit. We obtain the slope values, the levels of ground subsidence, and the areas with a high concentration of rocks, and we apply data to each patch. This information was translated into data points with distinct behaviors according to their attributes. Rock points became repulsive forces, while points with steep slopes and high subsidence act as attractor points. We employed a multi-agent system of simulation into the terrain that emulate natural patterns of movement. Through the attraction and repulsion behaviors, the agents generate emergent trajectories that respond to the terrain. The thousands of potential roads were produced, but agent-based modeling were fed into multiple objective optimization. We defined 5 objectives that were maximize the terrain stability, maximize the terrace area generating by the paths, minimize the corridor slope, and minimize the local length of paths and constraints. After the simulation, 1,000 of optimization results summarized in 4 design families using machine learning and select the optimal model that prioritizes our core values, stability and network redundancy. After all of this experiment, the refined network was projected onto the terrain, extracting all intersected patches for further analysis. From this process emerged what we call the risk corridor, a system with data about risk level into those patches.
The planting strategies are generated from the risk corridor by overlaying key ecological layers such as water accumulation, solar radiation, coal contamination, producing ecological data specific for the site. Here we convert the site environmental data into planting strategy. Each risk condition is paired with the plant group that can fix it, making the entire ecology data-driven. Similar divisions of 1.6 into 1.6 meter were made to allow more specific planting logic. The appropriate species adapt to the appropriate conditions, making the remediation effective. The next step illustrates the settlement areas from the buildable zones along the corridor. By combining risk intensity and the slope angles, the terrain is effectively prescripted to identify the patches that requires urgent stabilization. To achieve this, a K-medoid clustering algorithm was applied, which selects the representative patches from the dataset itself, defining the clusters of equal sizes. Once the large-scale data layers and the potential architectural patches were established, the cluster with the most hostile environmental conditions were selected for the further experimentation. Within the selected intervention site, risk and ecological data were combined with the additional site-specific layers, including pollution, potential water accumulation, and solar radiation, to support more informed and targeted design decisions. To define where architecture could meaningfully emerge, we developed what we refer to as volume of interest. For instance, areas with higher water accumulation prompt the system to grow down, and the areas with the lower risk values allow vertical expansion.
Well, this volume becomes a 3D spatial experiment of what is going to become an environmental intelligence. We filter this volume with the potential architectural patches from the cluster experiment. And finally, we select the more dense area. In order to measure this volume, we voxelize it, and we project the values from the previous experiment. We project the values of risk data, air pollution data. We project also the values from the ecological corridor. We also run the voxels according to its height location to measure the connection to the ground, and we run a radiation analysis into the voxels. So the key question here was, how can we evaluate each voxel individually? So we decided to develop an algorithm based on cellular automata logic. Rather than evaluating voxels in isolation, the system reacts data per voxels and generates simulations according to the values of its neighbor. We apply this logic of 3D voxels of the selected patch through iterative activation. We defined what we call points of interest, special voxels where future architectural decisions can begin.
The workflow outlines the regenerative sequence in which architecture will emerge from soil stabilization, planting, and environmental performances evolving through phase growth rather than the fixed form. To start with the stabilization layer, there are few site conditions first, such as site has steep slope, which collapses often. Fire burns underground, and the cracks open suddenly. Traditional methods cannot stabilize or build here. Where human labor cannot safely function, robotic camps can take over. They are able to print on steep, unstable terrain without risking lives. All material experiments are based on the locally available materials, keeping the cost low, reducing environmental impact, and these materials are already familiar to the local communities. We refine the soil by sieving and adding organic matter with hemp fibers to improve the cohesion. Water content was adjusted for printability, and lime and fly ash gave the mixed strength of the concrete while keeping its natural properties. Biochar and vermiculite improve the water retention for the plant growth, while 3% of alginate and bean gum strengthen the mix and the ensured printability. In the last experiment, the cohesion was a challenge. Increasing hemp content by just 20% enabled the mix to hold its form, performing successfully even on the steep slope. And the later various experiments performed on these material samples, where it showed gradual variation. The base mix with the strengthening and the bioreceptor additives perform well under the compression and the shear, and retain close to 10% water and maintain a pH from acidic to neutral. Out of all these samples, the last sample concluded to be the optimal mix, which then informed the next stage of the structural experiments. The fabrication method. This demonstrates the printing on the slope terrain. And lastly, we can see that optimal mix, how it acts with the terrain. These high-risk patches generates the intervention surface that is structurally evaluated using the values given by the optimal material properties. This resulting stress lines and the optimized column locations define the areas of required mass and structural support. The extracted stress lines are used to inform the generation of voids and the porosity. Void sizes and the distribution is varied according to the structural requirement and are selectively connected in relation to the plant species, which are defined by the ecological corridor. And this is the illustration of the first layer aggregation strategy of the robot printing.
To inform the mass to growth, a comparative study of plants dimension over the time was conducted across different functional types. This study told us that stabilization and soil enhancing species were identified as larger contributors of bigger biomass accumulation. Here we can see the proposal of this chapter, architecture and biomass become one. Roots descend as structural agents, weaving the wall into the terrain. So in this way, to define the mass aggregation, we start combining the experiments. We take the information of the planting logic from the corridor. We also take the information of the supports location for the bioreceptive wall, the biomass from the stabilizing plants and soil enriching plants, and the points of interest from the CA experiment. In order to generate result, we use agents again. So we define the seeds agents as the location of the supports. The repellent points were the trees to respect the biomass, and the points of interest as traditional attractors. So we ran a simulation of agents above the patch. As we can see, three-dimensional trajectories was given around the biomass. In this way, all the previous experiment informed the agent's behavior. We intersect this path with voxels of a grid of 1.5 per T meters in order to generate the spaces. This generates a volume and envelope of possible architecture. This diagram summarizes this process from the agent simulation to the volume. And once we have this geometry, we evaluate this geometry as an envelope with the structural performance, applying forces into the location of the supports. This analysis gave us stress lines into the envelope. We round agents using the trajectories of these stress lines. This approach is powerful because agents do not simply trace predefined paths. They introduce variation, negotiation, and emergence. The agent's paths become a spatial domain that updates the ecological values of the voxels. In this way, each voxels that initially used to generate this geometry has evolved and is now evaluated using the environmental parameters: solar radiation, wind speed, exposure to natural light, elevation, and spatial density. Using these updated voxel values, we apply a Gaussian clustering, a probabilistic method that groups elements based on likelihood and spatial proximity. This result is an adaptive internal organization that emerges from data-driven relationships. The activated voxels are clustered again according to their spatial coordinates x, y, and z, and become the coordinates of the spaces. In this way, what once existed purely as data is transformed into space. The data no longer describes space, it becomes it.
Once the spatial domain defined by the agent's trajectories and the interior data-driven spaces is established, these paths become the guiding framework for the mass aggregation. The aggregation process is informed by the biomass behavior and the ecological growth patterns. For year 1, robotic 3D printing of the earthen layers for initial stabilization. Year 5, second printed layers reinforcing terrain and the spatial continuity. Year 10, selective concrete casting to establish structural continuity. And for year 15, aggregation through the modular earthen components. The structure thickens, connects and adapts where the conditions allow it, remaining light or porous where the ecology requires openness. By following ecological and the spatial patterns of the aggregation, the project establishes the continuous dialogue between matter, time and environment, where the architecture involves with the nature rather than against it. According to the developed aggregation logic, we apply this methodology of agents, path, and emergent spaces in all the patches. In this way, aggregation logic is established and the mask grown in each patch. As we can see, each geometry is different because all the design have informed by the data. And the next step then is to understand the emergent interior spaces.
Once we have the total mass per patch, the interior volume is measured to evaluate the potential appropriation of these spaces. Using the same logic as the territorial scale, the interior spaces are subdivided into patches to quantify spatial capacity performance. We made a radiation analysis and we applied those values in each patch. We apply values of volume to the patches. Those patches associated with larger volumes receive higher ranks. Connectivity was also a key factor. The values were assigned to each patch based on the proximity between the center points of the spaces. We also identified those patches with more exposed wind according to the location. We can see decay of values in the interior. And we also apply moisture into the patches. This data was assigned according to the data of ventilation and radiation. The logic is that high airflow and high solar exposure produce drier environments. The next step is to cluster in those patches according to those values. And we define 3 distinct categories: human zones, transition zones, and vegetation zones. To define the zones, we developed the clustering algorithms based on set comfort criteria defined for the different environmental zones. Human areas require higher levels of ventilation and volume because the area is a tropical area, whereas transitional and vegetation zones prioritize humidity, reduced radiation, and moderate airflow. This classification does not define permanent programs, but degrees of possibility of appropriation derived from the environmental conditions. A space can be accessible at a moment and withdrawn at another, depending on ecological evolution. The diagram does not prescribe use, it maps opportunity. While the spaces allow zones for humans, they become one agent. Humans become one agent among others, adapting to the rhythms of living landscape rather than controlling it. This research explored how detailed environmental data, more focused into plants, comfort, can be translated into spatial logic, using computational tools to amplify natural process rather than override them. By privileging plant growth, soil recovery, and ecological performance, the project positioned architecture as an ally in the regeneration of degraded landscapes.
So what emerges here is not a building in the traditional sense, but a living geology, a landscape that learns from its own wounds and reshapes itself through the time. These spaces do not appear as designed, they appear as discovered, carved by data, shaped by ecological pressure, and softened by human presence. The architecture arises like terrain remembering how to breathe again. This thesis argues that the future architectural practice must engage more deeply with ecological intelligence, using advanced tools to design systems where the nature leads and humans learn to adapt. So the question could be, what if environmental systems and the ecological data became the primary drivers of the design and human presence emerged only when the conditions allow it?
Thank you.
I can go. Thank you very much. very lengthy process now, quite complex project, but really well presented. And I think you presented as clear as you could, which was very helpful. I have 2 points only. I mean, you touched on several design issues with a very innovative, analytical even approach. But I would focus on 2 aspects, which are very pragmatic ones. The first one is on the soil after that. Because I followed very well, I like a lot your process of regenerating the soil with the new layer of soil that you're putting in your agents, the whole landscape application. I thought that was really clear and convincing, very, very convincing. But then, as you probably know, the soil needs to keep on breathing. It needs light, it needs water, it needs air to keep on regenerating and renewing all the time and helping us with considerable good microclimates. The moment you start building the way you do in the final phase of the project, when you start proposing any habitation, I think there is a question of density and how much do you build that needs to be addressed. So maybe you can say something on that, exactly to keep the soil alive and doing its ecological functions. The second point has to do with the final massing that you show. I think it would be logical to imagine a decaying process of it, if we are talking about biological processes, ecological processes, but also a transformation of it. Because we know, not just in India, but around the global south, the living environments are transforming all the time, less shrinking, more expanding. So how does the project respond to that dynamics of density? And also, how do you guarantee that the soil will keep working as you initially proposed once you put your new layer on top? Is it clear? Yeah.
You want to? Yeah. Well, basically, because that was the main core of the project, that's why we add a lot of ecological materials to the composition of the wall, of the civilization wall. That's why we made a test of retention of water, and that's why also the porosity that was driving in this final output was, we try to reduce as much as we can from the structural process. And in terms of how these plants, because as you said, needs to breathe and all of this, that's why the way we experiment how the geometry was formed was using the bigger biomass from those stabilization and soil enriching plants. As we can say, they were the more dramatic area, the material volume, in order to repellent the mass itself. So that's more or less what we did. And related to the second question, well, basically, the core of this project is to use the data to tell us, hey, let's say the soil is telling us we need this, or can you prescribe this? So what we want is to speculate about the appropriation of this mass at the end.
That's fair enough. Thank you. Yeah.
I mean, very interesting project. Congratulations. Also very well presented. Also the static quality is very interesting. You know, this is a sort of emerging shape that really, you know, comes out of the process you've been describing. I think you know, it's very interesting your starting point, very contemporary, especially considering the risk analysis you've been doing. You know, how analytical you've been in identifying different risks. And I think this is an important part of contemporary architecture, a part of, you know, global conversation, especially here in UK after the new Building Safety Act. So I think it's a very important, you know, approach. I would suggest that as you have been so analytical in classifying risk at the beginning, would be also very important to have in your presentation also like a presentation of how you have been mitigating certain risk. Of course, you cannot assume you're going to resolve all the risk. You're going to remove completely the risk. You know, there'll be some risk that can be completely eliminated, some risk that will stay there. And I think it's good to have a sort of a way to describe that, you know, like we've been able to, you know, fully resolve this risk, fully eliminate this risk, but we still have, for example, you know, we can only partially address this type of risk. This is an important point. The other aspect I find is about the structural optimization you've been talking about. I think it's very interesting the way you're talking about analyzing stress into the terrain, analyze stress into the geometry. Some of the stress analysis you've been doing, you know, is clearly applies to specific structural topologies, like shell structure, for example. But the overall geometry you see here is actually more the result of a topological optimization. So I think it would be interesting to understand a little bit more how the structural analysis works, not only on the surface, but also in the three-dimensional, you know, volume of your project. You have it, so, you know, it would be interesting to document that as well. Another aspect of the project I think is very, very interesting is the fact that you want to regenerate the ground, stabilize the ground, and at the same time, you know, improve the quality of the terrain. And I think you are relying 80, 90% on the architecture factor. But I think the landscape factor should be, you know, made a little bit more protagonist in your presentation, because plants can bring nutrients to the terrain. So even explaining, you know, not just put plants as rendering assets, but, you know, choosing the right plants to bring back nutrients to the terrain, and choosing right plants that can reach certain depth to really stabilize the terrain, I think is an important aspect. Like there are some experimentation, for example, in China, to bring plants into the desert. They are also changing some properties of plants to, you know, have some plants that reach a certain depth, and this could be, you know, important because these sort of engineered plants can help, you know, deal with complex terrain and bring back some vegetation. Last aspect that I think would be interesting to see as well in the presentation is understanding when you create like a community, there are aspects of activation of life of the community that will be interesting to understand. So once you build the asset, you know, what is going to be the life in this space? So how, you know, why people are going to choose to go and live there, and, you know, how, you know, this, you know, is there. You can see that, you know, this sort of a building can bring different aspects of community life. But probably, you know, a diagram or something could help to understand what's the vision of, you know, community life in this new development, and, you know. But yeah, generally is a very great amount of work, and, you know, thanks for the presentation.
Well, about the plants, talking about the plants, we made a catalog where like we divided into 4 categories. First, the pioneer plants, stabilizing plants, soil enriching plants, and then long-term plants, which grows till 100 years. So based on that, like we studied like their height is, final height is till 15 meters, and their roots goes till 20 meters something. So it grows gradually till 15 years. So based on that, we made this porosity patches. The radius of the porosity is based on how large the plants can grow. And based on that, we also avoided the architecture patches. So it like covers, like it does not harm the plant growth. Yeah.
I think this is great, and I think having that in your final submission probably would be helpful because it's an important part of your thesis. So, you know, we didn't see this diagram here, but, you know, like clearly there was there, you know, something going on. So, but, you know, now that you say this, it's very exciting. So, thanks.
Okay, thank you for the presentation. It's a very interesting project. This kind of idea of ecological recolonization somehow. One of the things that I was thinking about your project was you're trying to generate these kind of new architectures that work with two worlds in a way, you know, so the kind of the traditional architectural world, building things for kind of humans, and then this more ecological oriented side, which, you know, speaks to nature, speaks to, you know, animals, and you showed it in your kind of last renderings. And I think it's a really interesting point, and I think these two worlds can definitely live together. But I'd like to understand a little bit more about how you actually make this possible. And I mean in a way that, for instance, when you talk about your settlements in the first place, when you start kind of using plants to add new kind of nutrients to the soil, it'll be good to understand then how you are kind of making those new, let's say, ecologies to work with the structural elements that will support ultimately the growth of architecture on top. But being, I will say, slightly more specific about it, you know, what are the actual loads that you're going to be able to resist, and then how that is going to become something resilient, let's say, you know, facing very harsh environmental conditions, you know, and the risks of the soil actually collapsing, you know, so how are you ensuring that this kind of new, let's call them architectures, can survive this kind of very harsh conditions and possible kind of movements of soil. And then the other thing is related to how do you enable these two worlds to actually thrive. So that means that what are the things that these new ecologies actually need in order to kind of thrive there? And then how are you implementing these things as part of your project? You know, and then when you talk about architecture, I will say kind of the same. You know, how are you ensuring, what are the kind of strategies that will enable this to actually support, you know, people to go there and do stuff, you know? So I think aesthetically it's appealing and it's interesting, but I wonder why, for instance, we're only seeing these structures to grow up, you know, why they're not growing in, for instance, you know? And was this something that you chose? Was this something that came from kind of your analysis? Was this something that came from whatever algorithm you were using? I'm just trying to think a little bit deeper in terms of, you know, the outputs you got, you know, and questioning them, you know. Are they actually fit for what you wanted them to be? I think it's worth kind of, yeah, maybe looking at them, you know, from a more kind of critical side, you know. But I think with the idea of kind of supporting the you know, the two worlds that you're proposing to live there, to, you know, to work, to thrive.
Basically related with the first part, once we have the risk corridor, what we picked, the patches that we picked in order to define the architecture were those patches with the most hostile values, because what we were achieving is to stabilize the soil. We didn't choose those patches with low values. The main core was to pick the most dramatic patches. So that's why all the locations where this architecture has been developed is in those patches. And basically about how we made this mass to be habitated, that's why we developed this clustering of the interior spaces about human zones, plant zones, and the transition zones. So what we wanted to show with that algorithm is demonstrate that humans can appropriate that, but at the end, it's not mandatory. We just show that there is that possibility in the project. Mm-hmm.
Thank you. I think it's very ambitious and provocative. I think I read the project as a provocation, you know? So do we need to do this to actually remediate? And I think perhaps you can frame it in that way. You know? Also because aesthetically, I like the fact that you're not staticizing. So very often you take a wasteland, very toxic place, and suddenly the architectural proposal is fantastic. It's the Eden. You know, it's paradise. And I like the way you're showing your project very raw. So I think my comments are about design, how you now assess the result. You're talking about agents. But there are moments where you turn the voxel diagram, and I understand you're using voxels as an efficient way of computing analysis and kind of reduce complexity. But then you embrace the voxel and it's the resulting. So it would be interesting to see if the geometries, resulting geometries can be softened, the idea of resolution, how you relate or translate the voxel diagram into kind of some sort of other tectonic language. And I was very happy to see all the fabrication and material experiments. That's great. But I see, tectonic-wise, I think there are two very different languages there, no? So maybe it can be curved, it can be the topography of the space. And then I guess whether it needs to be round, voxelized, cave-like, or perhaps you can look at the cultural values or the aspirations of the local people, no? So perhaps there are, 20 years of kind of non-human inhabitation. So while the place is being regenerated, and then after 20, 30, 40 years, then you can start inhabiting. But then perhaps you can interrogate what the locals would like to live like, what do they need to do. I need to be honest, I don't think it's easily inhabited. Maybe it doesn't need to be inhabited. But maybe there's, I don't know, sun movements or erosion or whatever, and then it becomes softer. So I think perhaps you can speculate in this potential timeline of inhabitation, and how would you match these? That at the moment it's more infrastructural, in my opinion, how it can become something a bit more gentle, more related to culture. But in any way, I think you've created a situation where all these conversations can take place, and I think it's very provocative to imagine how to inhabit this very, very hostile environment.
Yeah. So, while talking about how the design language changed from printing through the curves to the model aggregation, while doing the printing experiments, we realized the material requires some base. It requires some surface to hold on. So that made us think that if we want to move it vertically, we need some blocks. We need some like bricks that will aggregate and can take different shapes. So this is how that's why we made some casting base, and then after that the vertical structure can withstand on that.
Yeah.
The main idea was to just stabilize the land, which the printing base act as a foundation for this whole structure. Then the printing and this stabilization is mainly for the plants. So in this porosity, the plants can grow, and the architecture then can later build.
Yeah, this proposal is also based about meaning the material to be lighter. One is going to the top, to the bottom, to the top. That's why we pick, as Ajinke says, the bricks are smooth in order to be in the top areas after the creation process in 20 years.
Sorry, I just want to add something, because I do agree with you that this project can be read as a provocation, but I think we have to also take some responsibility about what we design and how we show it. And I think on the ecological side, I think there is a lot here, and I think your project can be quite strong on that side, and this could be a great way of kind of recolonizing, wasteland, or places that have been kind of deteriorated by time, by mining and other stuff, However, when you are trying to suggest human inhabitability for this, you have to really put the lens of architecture to this, and it's a critical one. So if you say, I'm going to build a building, but it's not mandatory for people to go there, I will say, why then you want to build it in the first place? Is that a good use of energy and resources? So I think my point is, if you do want to suggest that, you have to take enough responsibility from the technical side as well and say, well, this is how this can actually happen. And it's not, let's say, it doesn't have to be mandatory, but I wouldn't say it's just you can't just leave it by chance. You know?
Yeah. Well, yeah, actually,
That was a long discussion that we also had because we were saying, shall we say this about this? Shall we say this about this? And we agree with the comment because it also took us in different points several times, a lot of fights also. But basically, that's why at the end we cluster the spaces, and we also show how people can be inside, but we didn't develop that in a lot of detail because also we wanted to enjoy to speculate about this. Serious.
Yeah, I would like to add, I don't know who mentioned this word before, but somebody mentioned about this infrastructure part of the project that I think is a key word for this project. And I tend to agree that there is, you know, the point about, you know, should you invest resources to build something that, you know, like in a site that is difficult to inhabit? I think, you know, the aspect of landscape and using this technology you have also to let the nature, help nature to take back this land, I think the system you're using can do a lot. Now it's deploying everything vertically, and for sure, like if you let this stay there for 30 years, vegetation is going to grow inside. So you're going to have, you know, plant life that is going to produce oxygen, is going to absorb CO2, so it's going to do a lot. I think probably seeing some diagram of how this could happen horizontally and how the landscape can be part of this system a bit more, and how you can help nature, like you know, the reforestation that is happening on the desert is an example of that, how you create, for example, this square plantation to help trees to stay there. I think is an important aspect to justify, you know, a bit more the settlement. And I think in addition to the comment about inhabitation, of course, like the site itself is critical, but also like to have life in a community, you know, even if you solve local problems, you still have to create all the elements around that generate an economy for, you know, a community to live there and to connect, you know. So you need to probably think a little bit on the broader scale, on the master plan scale, how this connect with the rest of the territory, more like a, you know, territorial strategy, how to reconnect this site with the rest of the country, not only the local issue itself. Yeah.
Thank you.
So like idea about building settlement in this hazardous land was like the people near to these mining sites are living in the congested housing, and like there's like this huge land chunk is empty and which is also polluting the area around it. So while talking about the economy, like how we can generate economical activities for people, so people are their mostly labor is around the coal industry only. So building this, like if they work on this kind of the pilot project for this, like this abandoned mining sites, that can generate some new employment opportunities, such as they can learn about the robotic arms, or maybe how they can adapt to this new technology about this, how plants work to heal the soil, and that may allow us people to think about in broader aspects, how they can it can be like in this we only targeted this whole, like this small site in this whole mining belt of 11 different areas. So yeah, that was the idea, so like to start somewhere.
Thank you.
Hello everyone, we are presenting uncovering an interface between land and sea. So we'll go through 4 parts. First the domain, then the system framework, and then how we translate that system into our architectural moves, and finally we are concluding our conclusions. Starting with the domain part.
Mucilage formation is floating organic matter accumulation, which covers the sea surface and harming both marine system and coastal habitats. It often accumulates along coastlines and can be collected from the shore. It's a thick, static organic substance produced by excessive growth of microscopic algae. A dramatic mucilage bloom was observed in 2021. Its highest intensity occurred between July and August of that year.
Mucilage is not a single point problem. It emerges from interactive systems, land temperature rise, eutrophication, and stagnant waters. And reclamation strengthens the hard edge and reduces the circulation. So this is not only a marine issue, it is the urban coastal interface condition with ecological and economic impacts. We frame mucilage not as a cleanup problems, but as a spatial condition. Our proposal is multi-scalar network that increases water flow, permeability, and bioregenerative filtration, turning the reclaimed edge into a climatic and a civic gradient. Maltepe was selected as a design site based on criteria such as its proximity to ecological significant islands, and the large area of land reclamation, high density urbanization, and the occurrence of mucilage along its coast. Here, the reclamation acts as a thick buffer between the city and the sea. The coastline becomes a hard linear boundary, and connectivity is mostly visual rather than spatial. This landmark shows how the coast once worked as a shared public edge. Reclamation changes the ground condition and interrupts the original relationship between the city and the coast and water. Over time, the landmark gets absorbed inside the reclaimed territory. It becomes present but disconnected from the water edge.
The reclaimed land extends along the coast and deep into the sea, creating a large artificial platform. Now we move towards the system framework. We start with the stagnant water because reclamation directly slows the circulation and affects hydrodynamics. Based on those wind directions and speeds, fluid dynamics was analyzed through the existing bathymetry data. Outcome shows that there are high velocity areas, stagnant and highly stagnant areas. Based on this, high velocity points and stagnant points were defined on the reclamation edge. Our first optimization move is to redirect the energy channel water from the high velocity zones near the stagnant areas. The goal is not only not more channels, but targeting the connection that we break the stagnation. The final channel networks makes the reclamation land porous, so the coastal shifts from the hard barrier to the permeable gradient.
Bathymetry and hydrodynamics generate new coastal forces through the channel network, but the strong urban boundary still remains. So we now read the site as an overlap of urban social movements, forces and coastal water forces, and design where they can reconnect. As we move forward, our focus expands from water stagnation to land temperature rise as a major driver in our mucilage conditions.
The land surface temperature map shows a clear heat gradient, with the dense urban fabric recording the highest temperature. The code frames our approach environmental strategies fail when they address symptoms without understanding the system behavior. We use system thinking to connect the social and ecological and infrastructure as one independent spatial framework. Maltepe's land use and circulation shows how this dense growth and infrastructure have fragmented the open spaces and weakened the coastal connection. This makes connectivity and porosity a key, especially around the transport nodes where movement can be redirected towards the waterfront. This section shows how the urban coastal spine is split into the isolated zones by highway and the large hardscape surfaces.
Moving forward, the Susland master plan demonstrates how a vehicular-dominated interchange can evolve into a people-oriented waterfront without losing mobility performance. This diagram compresses the case study into 3 layers of what worked, what didn't, and what we learned from it. Those reflections becomes a direct design criteria for multi-pay, prioritizing the integration, real permeability, and a human-scale waterfront.
Here we tested how water actually moves through our channel geometry using flow paths to read circulation and that zone. The goal is to locate where water gets trapped early so we can adjust widths, connections, and openings before detailing it. Here we tested how water actually moves through our channel geometry. I'm sorry. The velocity map shows strong flow along the outer edges and inlet-outlet zones, while the inner pockets still fall into low flow conditions. That's the performance gap we target next, pulling energy into the pockets through strategic connections.
Now, two drivers together, coastal water forces shaping the pools and channels, and existing urban movements lines are trying to reach the shore. Where this intersect becomes a key design logic, nodes that are both hydrological, active, and socially meaningful.
The pedestrian and water network intersection within the boundary were mapped and used to select the curve. This generated multi-intersection points inside the boundary. The points along the waterfronts were used to bundle curves towards the pool areas, while the pedestrian intersection points at the boundary were used to bundle curves to the nearest existing road.
Then we brought in the ecological layer, especially the high temperature zones. By directing more water flow through these hotter areas, the system helps cool them down. The intersection points between the water network and the social network at the interface then become a key guiding forces, shaping how the water pathways respond to the ecological needs and urban use. The master water network begins at stagnant points, directs the flow through the high temperature zones for cooling, supports the existing green spaces, and then reconnects to the rivers. We later refined the network using our earlier insights on channel length and curvatures and bundled the routes based on the distance. In developing the social network, we incorporated not only tangible parameters but also intangible ones. Visibility becomes a major driver, ensuring the new interface connections maintain access to significant historical and experiential views. Shading was another key parameter. Given Istanbul's warm climate, the network can be oriented to generate more shaded zones and improve thermal comfort. Based on these two parameters, the heights of the water social interaction points and the force directions were derived, creating a set of 3D interface forces that informs the social connectivity. The master pedestrian network originates at existing crossroad junctions and transitions through the shaded interface zones, engages with the water pools, and extended towards the sea. It was later optimized based on the slope and the distance. Similarly, the vehicular network originates from the existing road systems, transitioning through the shaded segments, engages with the established pause areas, and proceeds towards the reclamation site. It was later optimized again based on the slopes and curve analysis. This overview of all three networks illustrates how their integration helps dissolves the rigid boundary between the existing urban condition and the reclamation. Once the connections were overlaid into the existing condition, we established the widths of the network. The water network applies the ratios informed by the Venturi principles, and social network expands at the intersection where more than two roads converges. There are three primary functions which are currently trapped within this interface boundary. The network was subsequently optimized around these three key functions within the interface boundary, increasing the connectivity with their vicinity while reducing it in less critical areas. Here we translate the project into a clear gradient from urban, interface, and reclamation. Across the three lenses, social, ecological, and experiential, it is basically our rule book for the architectural translation, what each zone needs to do and how the interface mediate between life, city life, and water performance. This section is where we translate our system framework into design decisions. This diagram shows like the translation as a progression across three aspects. In build, we start from the social layer. In activate, we shift to the ecological performance. And finally, articulate, we shape how people experience the gradient. We start with the social aspect. It is addressed mainly through the pedestrian network and control vehicular movement.
The transit hub journey was selected for deeper analysis because it carries the highest footfall, connects the multiple typologies, overlaps with the covered river, contains a rigid node that blocks the permeability and concentrates urban pressure, making it a key opportunity for strengthening the networks and reopening the connections. The urbanist theory of 5-element structure, how we experience the cities, they reveal the movement and identify where identity are shaped. This lens helps to diagnose the issue in journey and inform the design decision. The existing journey viewed through the same lens reveals the fragmented path, weak nodes, diluted district, sideline landmark, and rigid edges, highlighting where the journey breaks and where the intervention is needed. Here, spatial distribution is the input and the social intensity is the behavior. We want to control the control across urban interface and in reclamation condition. Based on the analysis, design strategies were designed by first demarcating the empty pockets along the edge to establish the new journey. This journey was then defined using the shortest walk logic, improving the connectivity and clarity, clarifying the primary movement path. The clarified route then led to the reconsidering the few buildings for the better support and maintaining the continuous flow. By overlapping the existing fabric, potential node locations were identified to manage urban pressure and strengthening the continuous connected journey. This is our final journey for pedestrian. Moving forward with the vehicle, it splits through the traffic from the local axis, reduce road dominance by prioritizing pedestrian continuity route. Vehicles therefore through the public anchors to improve the permeability. At the interface, the pedestrian path moves more towards the landmark to interact with the landmark which is currently sidelined. And vehicular path moves without disturbing this social junction. Extending this journey to the coastal permeability logic, merging a pedestrian route and merging a pedestrian route with the water channel edge, increasing dwelling capacity near the water along stay zones. The same logic was applied along the entire stretch, reconnecting the urban sea by integrating the existing fabric, increasing multi-level network connectivity and ultimately supporting the aim of blurring the rigid edge. At last, we added the build spatial mobility logic.
Now we move to the ecological aspect where water becomes the main performance system for the project. From historical water management systems, we extracted two operational archetypes, eruptive and the smooth motions. These two behaviors become a design vocabulary that we can position intentionally along the gradient depending on what each zone needs to perform. In ecological translation, the goal isn't water everywhere, but the right flow regime in the right place. Smooth flows supports the microclimate control in the urban zone. Mixed flows mediates the stagnation at the interface, and eruptive flow boosts the performance at the reclamation edge. So the output shift from the cooling and control exposure to the stagnation reduction to velocity, increasing the velocity for the water quality recovery. Based on the empty pockets boundary, we reintroduce the water as a targeted cooling system to reduce the stored heat through the evaporative effects and shaded microclimates. At the interface, these pools act as a mediation points. They support cooling from the urban sides and redirect the flow to reduce the stagnation. Here we use the Venturi principle as a controlled way to generate the eruptive behavior, accelerating water by shaping the channel length curvature, and cross-section. CFT becomes the feedback loop for the geometry is tuned through the clear objectives. The Venturi channel is not just a single form, but a search space tested against the performative objective. The selected outcomes balance the capture and discharge. Wider inlets improve the intake, longer balances the capture and longer throats sustains the acceleration, and narrower throats increase the peak velocity and mixing while avoiding backwater throughout the controlled flow. From water velocity analysis, we also observed that after application of channel morphology to the water network, it had helped to increase the water velocity. Moving forward, the reclamation will also address the problem of eutrophication. Globally, the seaweed cultivation is used to absorb this excess nutrients, and also at the same time, a biochar is well-researched material for nutrition absorption and pH balancing. Combining these two could allow us to design a local continuous nutrition removal system. To evaluate our materials, we focused on four key criteria based on their properties and the environmental permeability, cohesion, erosion, and strength. The experiments were designed in a different proportion with additional binders. Each stage was a response to the previous challenge, and through this progression, we identified the key distinction for the material optimization. From our experiments, we finalized the composites that maximizes the proportion of biochar for nutrition absorption. Using these rates, material proportions, and current ammonium levels, we determine the most efficient panel size. The panel's outer layer porosity is controlled with the grid-based layout, guided by the differential growth patterns, balancing the structural strength with the optimal water flow. Corrugation depth is tuned to the material composition, enhancing the filtration performance and durability in the marine environment. Now translating the spatial distribution into this experiential gradient, how water is perceived, approached, and finally inhabited across the urban interface and reclamation. These three scenes shows the same journey evolving from visual low contact water in the city to tactile, proximate access to the threshold, and finally immersive high contact water to the reclamation. Now, the formalizing the experiential strategy, we treat the sensory gradient as a dependent variable, meaning we intentionally design how sound, reflection, shade, and proximity evolve from the urban to edge.
Architectural morphologies were defined as a set of modular spatial elements responding to movements and environmental conditions. The catalog was applied through a gradient logic where morphological combinations vary in response to pedestrian-oriented conditions across urban, interface, and reclamation zones. In here, we can just see the relationship between the water and pedestrian.
In the urban zone, roads remain visible but are thickened architecture to act the canopies, providing the shade for the structured crossings for the pedestrian. At the interface, vehicular paths are wrapped with the acoustic shells to buffer sound and create a calm transitional spaces, while in the reclamation zone, they are pushed underground to preserve the open, undisturbed spaces. Thus, here, the vehicular infrastructure is progressively transferred from the surface roads to the urban zones and underground tunnels in the reclamation zones. Along this gradient, architectural elements such as canopies and acoustic shells are integrated to reduce the noise, provide shade, and gradually detaching the vehicular movement from the pedestrian water-oriented spaces.
Moving forward to the pedestrian and vehicular elevated structures at the interface, this sequence explains how the architectural system is structurally informed. Not just aesthetic, form is tested against the bending behavior and stress distributions. Further, the mesh density follows the force pass instead of the uniform thickness, and the material reduction strategy then translates into a realistic fabrication approach for the final architectural application.
And these are the section perspective moments of the vertical journey where water, vehicular, and pedestrian paths act as a part of the one system and shows relationship between them.
By activating the vacant plots along the coastal interface, enhancing the ground level accessibility through the use of mound spaces beneath the railways and the walkways under the highways, the proposal enables the water to re-enter the site and transform the previously fragmented boundaries into the coherent, resilient, and publicly engaging social ecological corridor. By activating the 3 nodes which are currently captured in this in the interface, the project tries to reflect the long-term framework and the urban development, where architecture meditates for the recovery. Thank you.
Okay, I'll go. Thank you so much for the presentation. Another really interesting project. I think through the presentation, I wasn't sure about the actual scale of this, but when you started kind of to present some of this kind of visioning studies about how this will look like in reality, I started to kind of realize how big this area was. And it made me kind of being a bit unsure about the kind of the actual site that you picked in terms of, is it, just to clarify something, is this something that is already built there, or
Yes.
this kind of rectangular area?
Yes, like rigid boundaries already in the area. So those rigid boundaries already in the area. So we are actually just...
And that is built?
Yes.
Okay, great. Yeah, because the first question was, well, if this is something that is existing,
yes.
You know, and then you are kind of applying these natural flows, let's say, to kind of reshape it in the first pass you did. Yeah. I was curious about why you decided to, let's say, retain the kind of the outer edge, you know, or kind of the overall shape, let's say this kind of rectangular, very rigid rectangular shape, you know, especially when you kind of presented this first analysis showing a lot of, let's say, acceleration in your CFD analysis towards the corners, which is kind of very predictable. Yeah, so I wasn't sure whether you were kind of proposing this or you were intervening something that was previously there. In both cases, though, I will say, well, if you have this as a canvas to interact with, you could have also questioned the canvas itself, you know, so you could have questioned the edges of this site, you know, and maybe thinking in a more integrated or in a stronger ecologically integrated project, you know, especially when you think about, you know, what the water is going to do, you know, in regards of the actual perimeter shape. Then the other thing is, again, going back to the scale. So when you start kind of using not only kind of the water flows, but then the pedestrian and the car kind of flows into your site, it wasn't too clear to me about how you were landing on those particular kind of curves, you know, kind of the paths that you describe. Especially when you think about something like a car, you know, so obviously people, car, and water flow different, you know, and respond to different things to actually flow. One's been more adaptable than others, you know, but also responding to a different, let's say, technology, right? And so I was unsure about how you were kind of dealing with this, you know, specifically when I see kind of the results for the paths for the roads, basically, in your master plan. It makes me kind of wonder why you have 2 roads or roads splitting into 3, you know, or going back together or turning one way or another. So it'll be good to understand a little bit more about what is driving kind of these roads. Are they trying to reach something? Are they trying to avoid something else? What's the logic behind them?
It's the, like we have considered also the intangible perspectives, like the visibility, the buildings that are the residential, when there's an interface between the reclamation and the existing city, and there is a visual connectivity to the monument there itself. So we have preserved that visibility and designed our roads in such a way. So those forces are creating those splits or the connectivity.
Great, thanks. I guess I was thinking more about your proposal, overall proposal, because I think it's not only about the roads, but it's how all these flows actually interact, but they're not only interacting between them. Okay, so this is not only a relationship between the water, the pedestrians, and the car. But it's actually, they're hopefully interacting with some sort of spatial qualities or program or something that you are kind of proposing for this massive area of the city. So yeah, I'd like to understand a little bit more about that.
So it's already a high density area, and we don't want to construct more of it, and we were planning to construct more of an experience-based spaces, so where people get the freedom to just have leisure activities out there in the reclamation. And as Istanbul was historical to be said as a city of water, but currently just because it's a concrete forest, there is no connectivity to the water at all. And there are less frequency in the water sports and that kind of thing. So it's better if they can, if the water is going inside, it also helps to mitigate the land temperature and also to reconnect with the people.
Thank you very much. I think I find the main premise of the project very attractive, this idea that the boundary between the city and the sea needs to be more porous, and then the idea of the ecotone comes to mind, or mangrove ecosystem. So perhaps you can reflect on what these ecotones or what a mangrove ecosystem does, what are the benefits for the species inhabiting it, to soil retention, kind of protecting from seawater rises. I think that's very attractive, and I buy it. The main question would be where these transitions on the ecotone needs to start, both in the city and in the sea. No, it's not clear to me why it starts so abruptly and why it finishes in that road, why it cannot be extended. So I think perhaps some consideration of where does it start, when does it stop. No?
So for the social network, like the pedestrian and the vehicular, it starts from the city itself where the cross junctions are, and they are coming towards the sea, like the reclamation part, to connect more them with the water, and the water part is going towards the sea to mitigate the heat, and also yeah.
I understood that, but I think you need to be much more precise, and perhaps there's different scenarios, and rather than kind of trying to convince us, use this more in an exploratory way. Yeah. In some instances, it would need to go 1 kilometer inland because, and then in some other instances, it just needs to enter 20 meters. So I think that's sort of a gradient, a more nuanced understanding, or an understanding of the system as a gradient. It's much more interesting as a way to explain the project. The other thing is that perhaps I think it's an experiment that is an experiment. I was kind of very interested in kind of the videos that you showed, the simulation. So I was thinking, oh, this looks very diagrammatic. But then you started showing these animations, these simulations, and they were very interesting. And I think perhaps rather than using these tools as a way to solve or to optimize, you can use them generatively. Some of the geometries were super interesting, and then you take one and analyze. Okay, does it work as a pedestrian network, or does it do what I want to do in terms of cooling or navigation? Does it work for a car? I mean, some of the curves and bends are quite sharp, so you can have many accident. So I think now you need to go back to first principles and assess very kind of simply, does it work as a pedestrian network, as a road network, as a channel network? Does it cool in the way and if not, it doesn't matter. Kind of you discuss how you would continue to push it. No? So I think rather than selling this as a salesman, yeah, it works, it does what, no, just be open about what works, what doesn't work, and how you would continue to push it. What are the limitations of the methods and tools that you're using? Because I think the approach is quite interesting, it's super valid. But it starts to become valid if you just try to convince us, yes, it works. I don't think so yet, but it can work. So how would you make it work?
Okay, I have 3 points I would like to put to you, and if you want to give me a feedback on these issues, I think we have a little time for that. I completely agree with the idea that the theme is extremely appealing, and for me, the focus on the pedestrian in these kind of cities, which are very, Istanbul, which is very car-driven, it's a great way to humanize it more and an opportunity to connect with nature as well. So the whole story, I think it makes a lot of sense. But I do have questions in specific aspects of your design process. The first one, if you allow me to put that, is I quite like to see the use of the CFD simulation to transform this reclaimed piece of land. But from the start, the way you open the channels, if you look the result of computed fluid dynamics, and that image is clear, it's almost counterintuitive to me that you cut the edges with smaller openings, and then you open somewhere in the middle where water will be stagnated, and then you try to go around. So when I look at that image, I would like to see, even if this is your starting point as a hypothesis, which I would question, because I think we should start with bigger openings and then start shaping it or tapering it, thinking of the principles of aerodynamics or fluid dynamics. Even that, I would like to see, I think it would be useful for you to have alternatives to that. And when you say we start shaping the channels, it wasn't very clear to me how many options did you look and how do you compare, or how did you compare them? At some point you talk about velocity, but then how much do you need to do the nutrients distribution? And more, do people meant to be in this water to go in? So what kind of speed do you want? So you do have a multi-criteria approach, which I think is great, but it's not for me clearly reflected in the scenario you're picking and moving forward with. So, and straight away, if we want to work with dynamics, or fluid dynamics in that case, why your edges are why your shape is so clearly rigid, because it is. So that's a point. Maybe you want to comment on that. It sounds a bit critical, but I think I would like to hear your views on this. The second point is when we talk about, and you emphasize it a lot, that's why I'm bringing this topic now. When you talk about pedestrian comfort in a climate like this, it's not one condition. So I would like to have heard a little bit about the climate. What comfort are we aiming? What conditions do we need to mediate? I mean, it's clearly a place of distinctive conditions through the year. So summer and winter are completely different environments. And if we are looking at public space, I don't think we should design for one condition only. Or you start from that, but then you see what happens in the rest of the year when climate changes. So there's a lot of emphasis on shade, which I understand, but you also want the sun. What happens with the spaces when the climate changes then? I think that reflection is important. And you probably know, if we're talking about comfort, it's radiation and air movement. Temperature makes very little difference. And that's why you're dealing with shading. But then you don't shade everything, of course. But the areas you don't shade, the ground conditions are very important. Material, color, water absorption, reflections. So the whole ground condition needs to be addressed. The materiality of it, the treatment of it, if you really want to have a completed approach on comfort. So I missed that part. From the images, I can infer that you have some ideas in mind. You don't need to test everything technically, but I think you need to say, what is it made of? How are those surfaces behaving? And then, the last point is, I go back to the design of the reclaimed land and the approach to water. As you go in the territory, in the mainland, and you want to work with water to moderate microclimatic conditions, you don't need you don't need the channels in. You need a very thin layer of water to have a positive impact. So maybe we are talking about water ponds that don't need to be connected directly with the carved channels that you have in your reclaimed land. So I think this subject of the microclimate modifications you want to create and the experience you want to create needs a little bit of a more in-depth analysis. What do you really need to do? Because again, to use water in that way, you just need a thin layer. So why are we connecting with the channels all the way from the reclaimed land? You can do something much simpler and effective. I think I stop here. In summary, I think the design of the spaces in the reclaimed land maybe can have more reflections on alternatives. The use of the CFD technique should be more informative. And then when you talk about the pedestrian, maybe you can capture moments, a day in the summer, a day in the winter. What is the journey? How does it feel like? Because really when we talk about these issues, we need to unpack in different moments to be clear about the experience. Yeah.
Thanks for the nice presentation. I have a couple of questions. So if I understand correctly, the land reclamation is already there. It's been already built. Yes. And do you know why historically they've done it, and what earth has been used, what material has been used to build it? Do you know anything of this?
Yes. So the majorly it's the concrete, and it's creating. That's why the hard edge, and there is very dense population and urban growth in the Maltepe region, and that's why and there are also earthquake, but there is no open space to people to escape from that. So they have created this entire reclamation land, which is just right now the whole reclamation is just a park right now. Okay,
that's very interesting. I think, I find first of all, the design topic, is tackling like a very, important environmental phenomenon that, affects, I think, it's applicable. If you find a solution to this, it's applicable in different countries, And I think it's also interesting the sort of urban landscape you achieve at the end in your three-dimensional views. For me, what would be interesting, to understand a little bit more is, how you are controlling this movement of water and how you are obtaining this connection, this network between the water and the pedestrian path. For example, you talk about, fluid velocity, right? But I think it's also important to understand, fluid direction, because the sea is always going two direction, right? A wave is putting pressure in one direction, but then, this is the return wave that actually takes the water away. So I think it's very important to understand that it's a sort of it's like working like a heart, right? It's like pumping water in, pumping water out, and how these interact with the water that is going to come from the land, right? So for example, did you do some hydrological analysis of the orography of the terrain? What are going to be the main veins, where the water during heavy rain is going to concentrate, how the the orography of the terrain has been evolving and how, let's say, these water streams coming from the terrain could be reconnected to, this end portion. Because maybe instead of superimposing a pattern, you could actually have let's say, a pattern that emerge from what already the orography is doing from the levels, and then, build on top of it. This, I think, it could be a way of justifying, understanding, the relationship between the water coming from the earth and the water coming from the sea, and how the two different pressure of the water are going to interact, and how this work with your system of cleaning the, the water.
So we first carve out the reclamation part, but and we also did the study. But the Sea of Marmara is an inland sea which have very, very low velocity. So just carving out and making a water circulation is not enough. So that's why we designed the channels based on the Venturi principles, which will increase the turbulence, and that will help us to achieve more velocity inside the city, and also circulating the water. There are currently 2 rivers which are covered within the city, so those channels then passes through the city and merge through those rivers, so it also creates the circulation. So it is not just creating a pools or where the water is getting collected, but it is continuously flowing through the city. So there is no stagnant points. So this we have just opened up the pools in the urban spaces and not the entire way, but it is moving below the city. So it also helps to mitigate the land temperature.
Yeah, that's interesting. I think it is interesting also, would be interesting also to understand the level of, I understand this is going to go under the ground, but it would be interesting also to understand how much energy you need to keep the system constantly moving, and, if the energy you spend to do that, balance the positive impact it's having on the environment. So I think this aspect could be, explored a bit more in the presentation to make sure that we understand the benchmark of, we do this and we gain this, but we need to invest this. And I think this is an important aspect. The other thing I would probably consider is understanding, what is going to be the urban, quality aesthetics of this addition to the city, because you say now there is already a park there. So understanding how these, will allow the population to a bit more to use these spaces, how these spaces, because, the images that you mentioned, images are very interesting, but it would be interesting also to understand what function are going to be there, that are going to attract people, that are going to make these alive, and, a continuation of the city, like an expansion of the city itself.
So currently at this space, there are very much of a temporary market or the seasonal markets happening, and people just go to the reclamation because there is a very less connectivity from the city to the reclamation, and it's a very but there is a huge market culture in the Maltepe region, and that's what we are aiming for, like how people can have like seasonal markets. It's not a need temporary permanent structure there, and allocating a function there, but it can be a spatial form where a spatial space where people can just interact how they want.
Yeah, that's very interesting. I think this would be nice, to see in a sort of diagram to understand, how these, will integrate with the existing city after you do your project. Yeah, thanks.
Sorry, just one more thing. Maybe something that will help you to explain your project will be to have some sort of a topographical plan. Something that clearly shows the levels that you have there. Just by looking at your previous slide, you said you are kind of 6 meters below the level of the city you want to get to with the water. So that involves a lot of movement of water. A lot of energy to move that water up. So having that kind of topography clearly explained or expressed in your plan views will really help you, as well as us, to kind of really understand how your kind of design, in a way, takes this into consideration. and reacts to that, and also is going to make things easier for us to understand in terms of how the spatial organization of this. Yeah.
Thank you. Thank you.
Good afternoon, everyone. This is Team Arkora. I'm Bhaskar Bharatwaj, and this is my friend Nikhil. Majuli, a river island that grows, dissolves, and reappears with the shifting modes of Brahmaputra, surviving through an ongoing dialogue with time. Monsoons carve pieces of it away, and the dry seasons patiently rebuilds them through slow deposits of silts. The fragile rhythm of loss and renewal became the starting point of our research, promoting a central question: can architecture adapt with the land rather than opposing it? In the MSc phase, Majuli was approached as a living ecology, the landscape where hydrological forces, sedimentation, and human settlement continuously shape one another. Computational design tools helped us simulate this natural intelligence, how landforms emerge, stabilize, and transform, and how the architecture system might learn from these behaviors. Through the evolutionary modeling, optimization, and visualization techniques, the design framework was tuned to real environmental data, tracing patterns of growth, adaptations, decay within the single interconnected system. The design evolved from hydrological analysis, where the river parameters were extracted through the CFD tools, which were then propagated throughout the site, which is selected, and this is done through the trained multivariate linear regression machine learning model. This resulted in specific points with a high sedimentation possibility. Sediments captured were placed strategically in these points to hold a feasible sediment volume. These structures were designed and optimized topologically and made into a lattice work for its functional purposes. And they were going through structural optimization through withstand multi-directional loads under a constantly moving water body. The substructures hold a key responsibility of withstanding a live load from the habitable architecture on top of them, which demanded for their structural integrity and wise material choice. Two complementary pathways inform the structural strategy: bamboo systems, testing for waterproofing, joinery logic, and structural resilience, and the earthen panel system, which is clay, silt, sand composites, assess for compression strength, water resistance, and modular assembly. The resulting bamboo earth modular system supports local fabrication, simple repair and replacement, and a minimal ecological footprint. Architecture here is not an object, but an active participant in the island's ecological rhythm. What emerged was a self-evolving system where land and architecture continuously shape each other. Yet it remains an abstraction, simulating behaviors without addressing lived reality. The next phase shifts from speculations to manifestation, translating adaptive systems into real structures, materials, and spatial experience. The hypothesis now sees the final settlement as a forensic reading, the way to decode and rebuild the logic of its own beginning. The settlement is therefore both prediction and archive, a landscape that remembers how it was made. Over the course of 11 years, the sedimentation process, the landscape gradually changes from the initial bamboo frame sediment captures to a community-driven hydrological system through proto-ground stabilization. Eventually, it becomes a cultivable land and habitable area where architecture and the nature coexist peacefully.
Moving forward, the presentation outlines the site's development trajectory, followed by the spatial logic governing the aggregation of architectural clusters. It then examines the extraction and the analysis of environmental gradient data that inform substructure placement in the initial phase, before concluding with the long-term evolution of the settlement across a 11-year timeline. We developed the project across 4 interconnected scales: settlement, aggregation, module, and elemental. Looking into the settlement study, the Majuli region features 4 key activity zones: communal, market, residential, and tourism areas. Each embodies the island's cultural and ecological essence, from silted flood-resilient homes and a lively market to shared gathering spaces. Relationship between local residents and tourists across 4 activity zones in Majuli have been analyzed. Each zone reflects varying population ratios and key functions, from local gatherings and to trade to living spaces and cultural tourism, illustrating the island's balance between community life and visitor engagement. The diverse tradition occupation that sustains Majuli's communities, which not only support their local economy, but also preserve the island's cultural heritage, craftsmanship, and deep-rooted connections with the natural environment. Majuli's festival reflect its deep cultural and spiritual heritage. These festivals showcase the island's artistic vitality, uniting communities through dance, drama, and music. There is a notable spike in the foot traffic that occurs during the festival months. This raised a crucial question: how did Majuli and its people accommodate and adapt to these seasonal surges? The layout translates Majuli's adaptive spirit into spatial form, where microzoning interweaves residential, communal, and tourism functions into cohesive walkable clusters. This hybrid planning approach allows traditional settlements logic to evolve with the contemporary needs, fostering cultural continuity, flood resilience, and sustainable community growth. The microzoning strategy ensures compact, walkable neighborhoods where living, trade, and cultural activities coexist. The plan showcases a hybrid planning approach with Namgas forming spiritual anchors surrounded by residential, communal, and tourism zones. The extracted design principles evolve into measurable performance goals, optimizing spatial relationship, minimizing travel distance, and analyzing environmental factors like velocity and turbulence data. Using the principle extracted from the existing plan, this rule-based system organizes residential, cultural, and tourist zones, ensuring maximum spatial relationship, reflecting Majuli's function, hierarchy, and contextual balance. Water velocity patterns and key distance reveal safe, efficient spatial arrangements, helping identifying stable zones, improving circulations, and guide environmentally responsive placement of programs. The derived layout interprets Majuli's existing spatial framework through computational logic, translating its monastic, residential, and communal relationship into data-driven spatial rules. Coming with the sedimentation concept, we had built a sedimentation tank experiment with a controlled flow conditions to reveal how sediments move, settle, and accumulate around obstacles. Flow speed and inlet position and substrate depth allow repeatable testing. Water enters the tank at a steady velocity, transporting sediments across the surface. As obstacles disrupt the current and deposition and scour develop measurable patterns. Once the flow is halted, the resulting terrain is scanned to document how it shifts in velocity, turbulence, and eddies, and shape the sediment around it. Obstacle generates wake zones, split flows, and creates downstream pockets of accumulation. Increasing the number of arrangement of blocks intensifies interaction, flow diverge, collide, and rejoin, producing layer deposition. Higher obstacle density creates richer sediment patterns. As more blocks disrupt the flow, turbulence increases, carving sharper channels and building thicker deposition zones. Sedimentation mapping defines phased growth. Phase 1 stabilizes the core, while the phase 2 expands outward along the emerging sediment ridges for adaptive development. Majuli's sedimentation concept guides phased growth, a stable core in phase 1, clustered expansion in phase 2, and a fully adaptive spread in phase 3. This inference plays a crucial data when it's overlaid with the developed datascape, creating the sediment evolution program. Moving on with the site development.
The site terrain evolves through layered analysis. The datascape establishes the base framework, the sediment gradient guides spatial response, and the terrain layer integrates these behaviors. Water flow mapping identifies channels and catchment zones, while green patches placements emerges from these combined environmental logics. As sediment accumulates and stabilizes over 1, 2, 1, 3, 5, and 11th year, vegetation expands from core zones to peripheral areas. Each phase introduces high-density planting points, strengthening ecological resilience and supporting gradual land maturation. Green patches grow in response to wetlands and sediment behavior, anchoring unstable edges as new land accumulates. Across phases, vegetation expands outward, strengthening emergent forms and guiding landscape organization. Let's take a look into the spatial planning. The experiment isolates high and low density with the optimization favoring the most compact high density outcomes on the best performing side. The truncated cube was divided into its component parts for its procedure based on its geometrical advantages in the context, and the modules were roughly categorized as circulation and bound elements to finalize this list. We carried out a number of experiments, trial aggregation exercises, which we will examine in the further slides. Here, the foundation of our spatial simulation is a 10 by 10 by 3 grid system of 3 cross 3 meter slots. In order to examine how created modules interact, cluster, and adapt in accordance to the previously stated fitness objectives and zoning logic, each cell serves as a testing slot. And then we modified certain linking logics and even attempted to add new modules to the system based on the findings. With a proper set of rules and modules in place, the optimization experiment is conducted across 20 generations and each generation size of 40. The objectives were to maximize floor area, decrease the fragmentation of the aggregation, and to increase the number of balcony units, which represents the stop in expansion. Following that, a clustering process is done to group together the solution which are in both extremes of the optimization, high and low density. And then these solutions within these clusters were evaluated against 4 parameters, which are open space percentage, walking distance, visual connectivity, and continuous floor area. Local units form the base. They regroup to minimize distance and improve connectivity. Clustering then tests options using floor area, movement visibility, and open space performance. These clusters show how the system adapts to different needs. Cultural units grow vertically and mix gathering spaces, workshops, and circulation. Residential clusters stay denser and more enclosed. Open and marketing clusters spread horizontally to support activity and flow. Each type keeps the same base logic but shifts form to fit its purpose. The low density units are designed to easy extension, allowing each clusters to grow, reorganize, and adapt to rapid environmental and social changes over time. These diagrams show how each cluster type can grow. The modules open, allowing cultural, market open, and residential system to plug in new units and adapt as need changes. Here, the extensions are consolidated into stable configurations. Each cluster settles into a functional layout while still keeping the flexibility to reorganize or expand in the future. Now let's take a look into the global scale development. The datascape maps slot density and functional distribution over the site. The experiment aims to understand and optimize how density and program distributes themselves in year 11, guided by visual connectivity, proximity, and the potential of sediment-driven clustering. To achieve this, the project deploys 8 distinct unit typologies, each derived from the outcomes of the previous experiments. The aggregation process follows a functional hierarchy, optimized to maximum proximity and density within the high density zones while maintaining strong visual connectivity across the settlement. The programmatic clusters distribute across the terrain and they self-organize based on flow behavior, connectivity, and sedimentation potential. Each clusters respond to site condition, creating a settlement pattern that adapts to landscape changes while supporting community functions. Now let's examine the extraction and analysis of environmental gradient data. Here, the distribution of functions across the site is visualized alongside the density gradient of the clusters. High density areas indicate older, fully established clusters, while low density zones represent newly formed or emerging constructions. The density gradient is then overlapped on the sediment evolution diagram, hence establishing a connection between the timeline and the density. The substructure appear in phases, starting with a low density base and gradually layered in more complexity. Each phase adds stability, new connections, and rooms for additional programs, shaping how the larger system evolves over time. Yet this raised a crucial question about the substructure, which are submerged over the period of time. To address this, sedimentation gradient developed from the river parameters and the machine learning model in the MSE phase is overlapped with sediment gradient from the developed spatial plan.
This process results in gradient that represents sediment persistence across the site. SPI. The higher SPI values indicate areas with greater sediment stability and consequently higher suitability for substructure placement. With the data set established, the chronological evolution of both the settlement and the sediment dynamics is visualized. Now we look into the evolution of settlements over the period of 11 years. In the initial phase, the settlement remains predominantly over the water bound, characterized by its aquatic livelihoods, shallow sediment capture, and water-based circulation, operating as largely self-sufficient functional program. Between the year 4 and year 7, the settlement transitions into a hybrid water-land system, where agriculture and engineered green infrastructure stabilize sediments and introduce early-based land functions. Looking into our section, the context comprises built zones accommodating the residential, cultural, associated functions along with open landscapes designated for agriculture use. These are interwoven with internal water channels and the structure circulation supports the programs. The cluster within the phase comprise both early and recent developments. Older clusters originating in the initial phase rely on substructure rather than conventional foundations and are partially submerged with accumulated sediments. In contrast, newly developed units are positioned on stabilized sediment layers and employ bamboo-based foundation systems. Now looking into the future projection and the materiality, we developed a limited kit of geometric components, each sized for manual assembly, repetition, and recombination. By restricting the system to a fewer adaptable elements, complexity emerges through aggregation rather than bespoke design. The same components scale into complete spatial unit through repetition. Quantities vary, but the rules stay consistent, allowing the spaces to grow, connect, or pause without changing the underlying system. After defining the kit of parts, the project moves into incremental assembly. The ground is prepared with a minimal intervention, then structural elements accumulates over time. Once occupied, the framework stays open-ended, allowing the users to adapt and modify as it emerges. With continued use, the system begins to self-optimize. Successfully spaces densify, underused elements are removed, and new components are added where needed. Over time, this cycle of use, adjustment, and regeneration maintains performance without relying on permanent form. Thank you.
Yeah, I mean, congratulations. The project is very well presented. It's very interesting. Also, like the way you created this animated diagram that showed the life of the project is very, very interesting. And the project is actually, yes, tackling like a very contemporary issue, like many of the projects before, like is this sort of flooding phenomena are now, you know, a major issue around the globe. Yes. So many communities will need to find solution for that. And there is a lot of, you know, vernacular intelligence here that you are bringing back on the table, and I think is very smart. I have just one question before I can make my comment, because it's something I'm still not fully clear. So when you show this transition between this sort of flooded area to the solid part, how do you expect this earth to be brought there? Is going to be human activity to bring and consolidate earth there, or is going to be something happening, you know, slowly over time?
Yes, answering that question, like this project starts with the human intervention on the flooded area, which is the river itself. So here we are basically building a substructure which has the capability to capture the sediments. So this over time grows into a feasible piece of land. I mean, again, people are involved in activities like stabilizing these lands over time. So initially, when there is complete water inside it, on the land, the people will be used to that kind of activities, and how their activities is evolving over the time when land is growing beneath them is the idea of the whole project.
Okay, that's very interesting. Yes, I think it would be interesting also in the first part of the project to see a little bit of analysis on how these floods are happening, understanding also the speed of water, because for example, what happens when you are in a bridge, let's say in a river, and you have, let's say, very strong flood, I mean, sometimes, you know, the action of the water can also like remove the earth around the foundation. So, and since I notice you have a pile foundation there, there is a lot about thinking around the sedimentation of the terrain. How this everything is connected to the capability of this development to find an anchor in this terrain. I think is important to have some analysis of, let's say, to some degree of application. So considering what are the risks of building in this sort of high flood risk areas, and to which degrees the system can be applied. Like for example, there will be areas in which the floods are very, very important. Maybe the speed of the water is too strong, and this development may not be applicable there. So understanding also in the presentation, what is the degree of application you expect of this system, I think would be interesting. The other aspect that comes to my mind is also like considering how the entire life cycle of this development, because a lot of this material seems to be natural material that are going to be strongly affected by the natural cycle of change of humidity, sun exposure. And for example, think about Venice, right? Because you are building a little Venice somehow, It works because the wooden piles are constantly underwater. In the moment you start to bring the wooden piles, outside of the water, you have cycles of load and unload of stress related to the fact that you add humidity, remove water, add water, remove water. Then, the wood will decay much more quickly than what happens if the wood stays underwater. So I think this consideration applied to these to the specific type of wood, I think, if I understand correctly, is all based on bamboo. So I think it's something to be considered. And also, I think a lot of the structure you're showing, like, create a sort of a rectangular frame. I don't see many, for example, diagonals to make like a closed structure. So I think since you're looking at vernacular architecture using bamboo, I think there are some examples. Would be interesting also to analyze, show at the beginning of the presentation, let's say, why you choose this system versus other vernacular system that use bamboo maybe in a more anisotropic way. So that could also respond to non-linear loads, like non-predictable loads, let's say. In flood condition, like, you don't know exactly what is going to be the situation that the system has to respond to. So I think it would be interesting to understand what has been what structural system you have been considering before choosing this one, and how do you expect in the overall life cycle of the project this material to behave, and what is also the lifespan you expect for this each block itself. Let's say, is it something supposed to stay there for 50 years? Is it something that is going to stay there for 100 years? So, because this will, help to frame the limit of your solution, understand, in which degree is applicable. But, it's very interesting. So thanks for the presentation.
Thank you.
Thank you.
Okay, I think Mattia already took most of my comments, but again, I think big congratulations. I think the project is fantastic. I think the presentation was great. I love all your diagrams, all the visuals. I think was very clear. It's just, a really, really good project and presentations. One thing I'll say, so just following up on this idea of the life cycle of the materials that you're using and the type of kind of organization that you're proposing, it's around this idea of the self-build. So I think you're working with a local material, bamboo, and then you are kind of proposing a kit of parts, let's say. Or a modular way of construction for the the locals to actually grow this in time. And then you have something going from kind of low density to high density to even kind of regeneration, disappearing in a way. It'll be really good for you to actually be precise about what's the actual lifespan of these materials, but also about the space you need to actually to produce this, to build this. You know, where are you taking the material from, and where are you working with this material? How you set up this kind of construction site in a way, it's kind of is a live construction site. It's something that is always under construction. You know, so I guess your typologies here, I was trying to look at them, but you have this kind of cultural, market, open, residential, and I think one of the key typologies here is about making, or should be at least. You know, so the constant fabrication, you know, or production of the space should be as important as other activities, I suppose, here. You know, also because if you want to react to unexpected kind of weather conditions at some point, you have to be, in order to be resilient, you will have to propose some sort of way to kind of quickly kind of reacting to that and rebuilding, let's say. So I think adding that information will be really helpful for your project.
Thank you.
Thank you.
Thank you very much. I think what I really like is that you're putting these very sophisticated tools and processes and thinking at the service of the least privileged. So that's very, very noble. That's very good, in my opinion. And I really like the output from a design point of view, from a tectonic point of view. But I would like you to reflect on whether this is fit for purpose in a tropical environment. So these processes and these tools that you've been using, very kind of clearly explained, done with care, do you think this is the best sort of geometry or arrangement in a tropical environment? How does your proposal compare with more vernacular, more traditional tropical architectures? Could this work in Tokyo? I think you've come up with a system, with a process, very well explained, and I think you need to now to assess whether this is fit for purpose or not. I mean, intuitively, I don't see big roofs, no, to create shading, to protect materials from lateral rain and ventilation. Fine. So I think at this point, if you ask, what if this happened somewhere else? Or how would you make this more adapted to the environment? And I think that the project has two distinct stages or parts, no? The sedimentation part, which is very clear, and perhaps you could do some animations, that you're very good animating things, so perhaps an animation that you place a seed and then sedimentation happens and then architecture can happen. No, I think that's very clear. And then perhaps greater integration, no, between what happens on the water, what happens above water. Is there a way that these two things can, I don't know, tectonically or aesthetically or formally relate to each other a bit, if it's necessary, no, as an exploration. I think overall it's a wonderful piece of work, but I think at this point you need to assess, okay, is this a good topical architecture? Also socially, I think you're condemning or you're associating different housing units to each other. Okay, you're going to see your neighbor. What's the agency they have? No, I don't want to see this neighbor because I don't get on well with them. So what are the kind of flexible parameters? How you can make this system adapt to or give the locals more agency, no? So again, what's your flexibility or how you're offering flexibility from a social, cultural point of view? But in any case, I think it's a great piece of work done with care, well communicated. Well done.
Yep, thank you.
Okay, thank you guys for the very comprehensive presentation. Immense amount of work, and I also like your take on the topic, that you really throw yourself and you produce a lot. And although it was a big amount of work, I think you presented with sufficient clarity. So I think this is great. I have a similar point to Nacho, if I can divide into two aspects. I mean, the tropicality of the project has to be mentioned. there's a lot of emphasis on the structure, on the logic of how you create your density, but the climate, especially in, let's say, a more low-income community, is such a strong force that there's no reason why not to make this an influential force as well. I say that, but at the same time, I see it between the lines of the project, how the climate has been addressed. So 2 points I think you could emphasize when you present, when you reflect on the project, is first on the urban or the master plan conditions that you create, because there's definitely a gradual increase. But the climate requires a movement. But it doesn't mean that we need completely detached units very far away from each other. But then the question is, what do you need in terms of porosity? Can you create the density with the porosity that you still need to then provide adequate thermal conditions indoors and outdoors? Very easy for you to answer that question. I mean, you don't even need to run simulations necessarily at that point, but you can look at what you produced and have hypotheses about the airflow between units. I would strongly recommend you to do that. I think it will bring a lot of value to the work. And can you densify then, keeping the porosity? So which are the openings, the voids that you safeguard and you don't invade with any density? And they are very important. And if they are also part of the social life and understood as key outdoor rooms, because indoor space is very compact and maybe less interesting even climatically than outdoor, you know, if you invert the logic and say much of the living happens outdoors because of the climate and need a minimum level of protection, but it happens outdoors, then this porosity is going to be protected because it will be understood as vital spaces for the community life. So I think it would be worth to reflect a little bit on these qualities that the project has, but you need to be more explicit about it. And in that quality, I think the relationship between indoor and outdoor in what you're creating is key. We see in the renders how emphasis you're giving to the occupation of this, even at platform level, of the open spaces. So maybe they are the key living spaces. So indoors is just for a very short period of time. And then as with your adaptability of components, it opens, and all of a sudden everything is an open space. But I can see the potential there, and I think it's fantastic that you are promoting the density and still creating, hypothetically at that point, enough porosity and a very symbiotic relationship between inside and outside. But if you can make that more explicit, the project will gain a lot of value, in my view. But thank you very much for the depth. Yeah.
Thank you.
I just want to add something. It's just that because your images are so beautiful, sometimes, you know, we get seduced by these things very quickly, and then, you know, it drives the conversations, you know, to the aesthetics rather than kind of the what's behind them. I think I just kept looking at this image that you put in front of us. You know, it will be good to, let's say, use this image and then look at it through different lenses. It's like applying filters to it to prove or to put, you know, kind of to test your thesis, you know. So through the lens of all the things you wanted to achieve, you can kind of use the same image and say, well, this works in this way or it doesn't work in this way. You know, I mean, you have like crazy kind of floating corridors that are unstructured. You have huge palm trees, you know, growing in your kind of settlement and things like that. So I'm not saying that your design necessarily will never support these things, you know. It's just about, again, taking responsibility of what you're presenting, you know, and it will make your idea stronger, you know. Even if you are kind of noting what are the areas that you are proposing, you know, that still need work or have been worked out, you know. So it'll be good for you to make it stronger in a way.
Yeah, I would like also to, you know, make more, you know, like to prize you, I mean, to provide you like a positive feedback on the analogic experiment you've been doing, because we have not been commenting that, but I think it's a very interesting thing, you know. I was very, very nice to see how you tested this, creating this sort of machine to test the sediment. It's all about your thesis. So I think very well done on that side, and also very well documented with those diagrams explaining how it works. So very well done. Since you've done so much work, I would like also to put there another couple of let's say inspirational point that could help you to add some diagram or some conversation. For example, considering aspect like how you're gonna collect water harvesting, because it's an important part of the farming side as well. How you're gonna because you're on the water, yes, but it's not so obvious to use that water. So how you're gonna collect, store that water, clean that water, use it for agricultural purposes, and maybe for the life of the project itself. Another critical aspect that probably I would try to at least show you have been thinking about that is, let's say, more like a risk-related aspect. For example, let's say how this material is going to work in case of fire. I know this is a bit beyond the scope of the thesis you're doing, but I think you've done so much that I think adding also this level of consideration will further increase the depth of your study. So considering also how what are the risks of this sort of development, and how this material, the structural system you have, is going to respond to different type of risks that may affect this sort of development. Yeah.
Yes.
Thank you. Thank you.
We can wait. Yeah.
Yeah. Hi, good afternoon. I'm Netra.
I'm Siddhi.
We are team living in the liminal. Rise in sea level threatens natural lagoonal edges. One such place is Chigu Lagoon in Taiwan, where the economy of nearly 15,000 people depends on oyster farming and tourism industry. Some processes taking place within the lagoon waters and other on the mainland, far apart from each other. But this ecosystem is under a serious threat. Shifting sandbars are narrowing the lagoon's width. while its depth decreases, leaving barely any usable area for oyster farms. In response, the government has built breakwaters on the sandbar, but these are all short-term solutions, sometimes causing more harm than good. Chigu's economy is majorly dependent on a seasonal oyster cycle. The oyster farming starts on the mainland and continues in the lagoon and in the water channel. Different farming techniques are used based on the lagoon depth. And finally, the oysters are harvested on the mainland again. The process is scattered. Inadequate infrastructure forces fishermen to live on boats, and the sandbar itself remains largely unused. Over the years, the sandbar's landward shift has shrunk the lagoon from 150 to 15 square kilometers. Now let us understand the source of this sediment that has formed the lagoon. In summer, the sediment movement is balanced. What goes in, goes out. But in winter, the sediment that enters the lagoon isn't fully flushed out and settles, shallowing it. To summarize, the first line of defense, the sand barrier, is eroding. Second, the sediment accumulation is shallowing the lagoon. Thirdly, the oyster farming processes are scattered. This leaves just a narrow pocket of lagoon deep enough to sustain a profitable oyster farming. For Phase A, we study the sand barrier and critique the government's short-term interventions that fight nature, and miss the link between coastal defense and aquaculture. What if we worked with those natural forces instead, integrating the two? By shifting key farming processes onto the sandbar, we can address fragmentation and enable a seasonal fisherman settlement that grows with the lagoon. The first phase looks at 4 research verticals, from jamming to interlocking, deployed across the sandbar. It starts by asking the question, how to grow land? Based on research by Skylar Tibbets, we learned how working with water flow can gradually build new terrain. What could those obstacles be? In our context, we tried to jam oyster shells, which failed. Looking at geometries more suitable for jamming, we moved to spicules. We simulated the stacking behavior to assess their stability and shortlisted some for further testing. We developed a sediment deposition and erosion prediction model of the sand particles, where red shows the deposition and white is the erosion. We evaluated the modules for their density and deposition with a platform on top for accessibility. These modules of 6-leg and 4-leg emerged as the most effective. For the obstacle geometry, the usual sequence, morphology design followed by a simulation-based evaluation, is a unidirectional process, and it does not allow for an inverse inquiry. So to address this limitation, we built a site-calibrated machine learning model that predicts erosion and deposition, allowing us to derive a geometry from the desired sediment behavior. So this is our chosen offshore platform geometry and its assembly logic. The modules are strung with anchors, lowered and tightened into position, and in situ hatchery units are added. These are the visuals.
The second research vertical focuses on using discarded oyster shells as the primary construction material. We set material targets based on density, strength, and tested those mixes accordingly. The final mixes were cast with a reusable formwork fabrication strategy. To test their life cycles underwater, each sample was kept under observation for a period of 90 days. The third research vertical plans a phased growth of settlement for 500 fishermen on the sandbar. We set certain goals, iterated the plans, and selected the one which balances all objectives. We also tested topological interlocking in funicular shell systems, used thrust network analysis to form find, and built 1:1 prototype with our oyster shell mix. Phase A of the research concludes with the growth of a sandbar. This sandbar seasonally hosts a fisherman's settlement made of interlocking oyster shell composite structures. Here we show the seasonal timeline. Fishermen start to assemble housing ahead of the farming cycle, and after 9 months on the sandbar, they retreat during the risky typhoon period, only to return for a fresh new farming cycle. This seasonal cycle is how our proposal makes sandbar living viable. For phase B of our research, we focus on lagoon shallowing. Over the years inside the lagoon, every possible inch has been used to oyster farm, which has led to serious overcrowding. Based on our findings, the most profitable technique, the floating oyster racks, are present in the deepest part of the lagoon, which produce adult oysters within a year. Since it's a highly productive lagoon, we tried to understand the relationship between the sediment buildup, overcrowding racks, and water flow. A CFD test was run to observe how stagnant the water inside the lagoon is. It was realized that this is all a low-velocity water problem, which could compromise future farming cycles. Looking at the current situation, we believe the need to intervene inside the lagoon. By introducing targeted erosion, we create deeper pockets in the lagoon, which can then host more productive floating oyster racks throughout the entire lagoon and not just in one small zone. With this intervention, we restore the lagoon by creating depth, increasing water flow, and opening up space. By deepening and decongesting the lagoon, we create space not only for water to move, but for people to engage. This is where ecological repair evolves into architectural possibility. Our hypothesis states mobile interventions in the lagoon can restore water flow while simultaneously supporting other activities.
To protect the lagoon, we first need to understand it. So we built a digital twin with points, lines, and vectors, each carrying depth and velocity intelligence. And we can use that to sculpt it. Now we had this lagoon packed with data. So for the first intervention, we chose one patch of the lagoon marked by the motorboat lanes and the tidal inlet. Here we identified two rules. First rule is based on water velocity to distance from the opening relationship, and we further divided them into velocity-based zones. Rule 2 looks at the depth and velocity relationships. So in a lagoon, points on the surface have higher velocity, and it decreases as the sediment gets closer to the lagoon bed due to friction. We further categorize them. We layered that data with an idea to intervene at points where water flows in moderate velocity. So with objectives to find out how can minimum intervention give us maximum erosion, we developed a multi-objective optimization. These are the possible locations of intervention. We applied the same logic across the entire lagoon and used optimization to identify intervention points capable of reshaping this lagoon bed. Now, what could those interventions be? We studied basics of scouring physics dependent on geometry. We went back to our obstacles and this time tested them to understand which orientation creates highest erosion using our sedimentation model. We observed the more the geometry forces the water to turn suddenly, the more erosion we get. The W-shaped geometry performed the best. We then developed an experiment to test which geometric configuration, the length, the orientation, and the angles could generate strongest water velocities at each intervention point. We ran CFD for 20 geometries and used that dataset to train a machine learning model that predicts local water velocity changes. We use increasing water velocity as the key objective that guides all optimization iterations. This configuration gives us the strongest erosion effect. It's interesting to see the scale as compared to the lagoon. Our proposal works on two timelines. Fixed platforms stay long-term to reshape the lagoon bed, while the floating platforms can reconfigure seasonally.
The next experiment builds on that, where we aggregate platforms, the obstacles to inhabit. We use DLA because it lets us grow a path that connects docks and intervention points, avoids floating oyster racks and high velocity zones. We gave some additional attractors some connectors, and left the walkers from the side boundary to walk the path. We identified 3 curves which satisfy all conditions. Next, curves are aggregated using scalar field-driven logic, where a 2D path and depth values directly link the system to the lagoon bed. Computationally, once a curve is placed in the 3D field of points, its distances to the points in the field are marked, and the points closest to the curve are selected. Then the points with the least depth are selected for aggregation first. These are the seed points for initiating the aggregation. Aggregation completes along the full curve, selectively skipping areas based on depth and velocity data. These aggregations represent only the possible positions for the modules and not the platform itself, merely a base state for spatial configuration.
We selected curve 3A because it sits inside the lagoon while still connecting back to the mainland. We developed a metadata system, a kind of DNA for each platform, defining its floating or fixed behavior, structural links, and distances. We set some rules. Floating modules close to the mainland are tagged as docks. Floating modules inside the lagoon close to the intervention points are used for monitoring. Fixed modules with many neighboring links are the markets. Smaller clusters of modules close to the markets are stalls, and all remaining active modules with less links become pathways. In Chigu Lagoon, spatial configuration shifts responding to climate, aquaculture cycles, community needs, and fluctuating tourist presence. We start by designing for the farming season, with the main objective being activating modules inside the lagoon. These are the balanced outcomes. We identified interesting spatial moments in the aggregations and chose that iteration. Similarly, for a low tourism season, new stall clusters start to emerge, responding to community needs. Here as well, we evaluated the moments closely in the aggregations for spatial combinations. In the festive season, when the tourist numbers peak, the objectives shift to support their needs while keeping the network fully connected. We chose the configuration that maximizes festive activity, high stall and market concentration. Well, for typhoon season, which demands retreat, we filtered for the least active and least exposed configurations from our previous experiments. Here we see a complete cycle. The transitions are driven by the metadata that governs what can stay fixed, what floats, and what must move next.
Moving on to the local scale. The platforms are designed to be of 3 categories: fixed modules resting above obstacles, anchored modules using built-in anchors for stability, and floating modules with no obstacles underneath. The platform is to be equipped with a frame, a detachable canopy, and 2 kinds of accessories, some built into each platform while others act as add-ons. Composed of 3 layers of bamboo, all parts can be swiftly assembled by 2 to 3 people in 4 easy steps. For the canopy design, we start with a base and a sketch of the frame. Using 3D graphic statics, a reciprocal force polyhedron is constructed, ensuring that the geometry admits a compression-only load path, which upon subdivision and reciprocal resolution returns with a force diagram. This helps in the design of the members, although final decision on the sizes is made after structural and lateral load displacement analysis. We experimented with force residual form finding simulation to assess the behavior of the structures when subjected to displacement of a critical load case scenario. The frame geometry is revisited in design to accommodate bamboo's materiality, weight, and bending. Most importantly, the frame is designed to be collapsible for easy transport and assembly. The frame may stay at a 50% state or be extended with bamboo for mid-level branching and attaching a canopy. The design also entails some easy-to-follow joineries for the anchors, posts, add-ons, and platform connections. A simplified kit of parts can be used to assemble the entire platform. This diagram demonstrates the platform's intuitive assembly, use, and disassembly sequence supporting mobility. At the regional scale, pathway typologies are established first, forming the base layer for all spatial activities. These are potential market stall configurations defined by capacity, sizes, and assembled using add-on accessories. Monitoring stations integrate with oyster farming zones to support stringing, drying, and other daily operations. On the screen are some possible dock and rest stop configurations for boat access and pause points in the lagoon. Hence, a single platform logic enables multiple spatial roles. Yet the most exciting aspect is the ability of the platforms to change their spatial and structural affiliation to suit the changing scenarios across one farming cycle. By straightforward modifications, two material systems, different functions and requirements can be fulfilled. This is our mobile infrastructure. To support this mobility, we propose a digital guide that translates platform metadata into usable information for everyday decision-making. Users can access platform-specific information, including its type, location, usage, history, and other maintenance data. Well, the project doesn't end here.
After the first cycle has achieved its targeted erosion, a new cycle is initiated, reapplying the same logic to a transformed landscape. To understand how to transition from one season to the next, we begin by identifying redundant platforms and start removing them sequentially. The platforms are removed by means of motorboats towards maintenance and storage areas. And this is how the next state is achieved. Overall, the platforms trace a journey of transition, starting from low tourism to a highly productive festive season, through a typhoonal retreat, finally culminating in the farming season, only to start all over again. In our proposal, change begins with sedimentation, a change in flow of water, change in the locations, change in spatial qualities. It's a cascading effect. It is interesting to imagine this is how it looks one day. 3 months later, that's how it could look. And a few months later, things would be so different. From sand barrier to the lagoon, our proposal is a system guided by depth, flow, and seasonality, turning restoration into activation and activation into economic renewal. It is a living project. This is living in the liminal. Thank you.
Thank you.
Thank you very much. Fantastic presentation, really clear. The focus and the clarity, commendable for me. I really like the way the proposal and the study stays close to the first question, which is the conditions in the lagoon. I wasn't even expecting so much work on the design of the unit itself. And 2 people, group only. So incredible amount of work. The only comment I have, well, just like you said, I think you ended your final words. You contemplated all the variables from the context, from social to environment, that should inform this project. And I think they are all there very clearly and well related. Maybe looking back, something that I would like to ask you, if you had any insights on that, is the module. And well, one thing is about the module, because you start working with that hexagonal module. and as you put it together, you have, let's say, global shapes on the surface of the lagoon that maybe could be resolved or built even easily or quicker with other kinds of modularity logic. So because you start from the module and then you have an entire surface and then go back and is this the best way, including all the variations that, or the changes that your entire platform goes through in a season. So that's a question. And also the activities and the stress of, if you can put some stress in your, let's say, optimized platform, meaning you have a number of modules, a certain surface area that you need to cover to create to control the erosion the way you want it.
Yes.
But is this a case of optimization or is it a range? And that's something that I would like to reflect on or hear your thoughts.
Yep.
There's probably the area that you are covering and even the position of your surface, it could change. It could be 10% in this direction or 15% less in that other direction, and we'll still get the result you wanted. Yeah. So I'm here challenging the idea of optimization as a final form or number to achieve what you need. Mm-hmm. You know what I mean? I think it's more, well, that's the point. Do we really need an optimized surface, or there is a range in the surface that you can work with, and that could respond to maybe less material source in a certain year, or more in another year, or also expanding to have wider areas for certain activities in a certain time of the year, and not be so limited to the optimization of the erosion control. I think it's a fantastic initial point and needed. But maybe rather than a fixed area, there is a range of and a variation of shape that you can work with. Sorry, I think it was too long question. But.
Yeah. To respond to the first question, if the arrangement of the modules is the best way, as it happens that the arrangement has to fulfill two functions. First is what is happening above water, which is social and access and navigation, and the other is what is happening below water, which is erosion and scouring. So taking in consideration these two functions, when they are put together, that is the best proposed arrangement that comes forward. Yeah. And for the second question, which was more related to optimization, the scouring or the erosion, more than optimization, I think the appropriate terminology would be target scouring, because we have assessed areas and identified certain targets, and all of the other processes are intended to work towards this target. And once the target is achieved, then it sort of resets, and there's a new cycle is issued.
Yeah, so we cannot predict how much erosion occurs, but we have tried to identify that would be the location to place those modules in and achieve certain possible erosion. Yeah.
Thank you very much. I agree. Super clear, easy to follow, and convincing presentation. I have to say the kind of the infrastructural part and all the work you've done with the lagoon it's impeccable. No, I mean, it's great, and it's quite. I mean, I'm surprised with this kind of level of intelligence, sophistication in the kind of analytical and kind of infrastructural design process, and then the constraint and the humbleness of what you're proposing. No? So yeah. It's a very high-tech design process and a very low-tech construction system. No? And I think it would be nice to reflect on this, and kind of in the broader context of the discipline. Do you think this is the way forward? And I mean, is there margin to continue designing the platforms? I don't know, so they become more culturally relevant, or so I think it would be nice to understand, to hear your thoughts about why does it need to be so contained, no? So simple. I mean,
In our case, our project was extremely contextual, and we wanted to keep our architecture as close to them as possible. And in a way, oyster farmers already have a really hectic schedule and hectic work-related things they need to do. So we didn't want our architecture to be an additional work. You know, it should just be a part of their everyday routine. So that's the reason we chose to stick to easy and vernacular way of constructing.
Yeah, so it's a purely logistical reason. And in addition to that, of course, there would also be other aspects like the governance structures, the maintenance responsibilities. So in order to simplify all of those, it's best if the architecture itself is rather intuitive.
Yeah.
So you're assuming this is a kind of a bottom-up initiative. This is
Yes.
something that it's initiated by, which brings the question, they didn't cause any of the modifications or the kind of phenomena happening here, no? So I think it brings the question, could this be something organized from the government or from institutions? So there is, I don't know, they don't need to self-build it. So I think perhaps in terms of governance, in terms of agency, the context or the economic or political context of the project could be explored, no? I mean, in your conclusions, to make it even stronger, no?
Yes,
so
right.
I think it's already a very, very strong piece of work. Thank you very much.
Thank you so
Thank
much.
you.
Yeah, thanks so much for the presentation. It was a really clear presentation, really clear. The ability to focus on 3 key problems, and then even though you were addressing really complex problems, you were able to achieve a very simple solution. That means that you managed to embed a lot of intelligence in your project and make it happen. You know, so we could clearly see it without, you know, many lengthy explanations. So congratulations. I love the fact that you were able to go all the way from data and ecology to ideas to actually physical experiments. I think it's an amazing piece of work. So yeah, really congratulations. I think one of the areas that I found really interesting on this project is how it plays with time. So your main problems come as a product of, let's say, a time lapse. You know, so erosion as the main thing that you're trying to deal with, you know, kind of evolves or changes, you know, obviously through time. And your solution, in a way, it's adaptable and reacts to that.
Yes.
But I wonder if at the moment your solution, or by look of it, it comes from, let's say, digital analysis
Yes.
of the problem. Okay, and so so the solution is great, you know, but when you start projecting in time after this has been, let's say, implemented, and I know you showed us some kind of, you said, okay, well, we reach our kind of target and then we reset and start going. That moment, it happens physically.
Yes.
Once this is deployed. Okay, it's no longer necessarily a purely digital
Yes.
kind of task. And so I wonder what will be, let's say, this your way to actually tracking, okay, the evolution of your project in time to kind of feedback, you know, to your kind of strategy, and then reshape, you know, the project to the next kind of session, you know. And I'm also thinking it may not only be erosion,
Yes.
okay, because you also talk about deposition.
Yep.
Because you have permanent structures, you know, you will have also sand and other stuff growing there. That may change, you know, how the water flows, the speed of it, and so on. So all the parameters that you took into consideration may be affected by this. And it will be really good to propose or acknowledge, at least, a way of kind of physical tracking, in a simple way. And then maybe kind of thinking in what Nacho was saying about what are the mechanisms to implement this. It's also key because you for instance, you show this kind of app, to self-build these things, which is great, but you will need, again, kind of a connection between, let's say, the digital world or the untrained kind of labor, and this kind of physical tracking, you know. So whatever technology you're using, it needs to be both kind of implemented by someone and then maintained and understood by somebody else, So those are kind of key things. And then the last thing, also related to time, I wanted to mention is it'll be good to understand a scenario going step by step through the change. I mean, specifically when you show these are the modules that are permanent, okay, and we see kind of these little islands in the middle of the sea, and then this is how it grows. And I wonder, how will people get to the islands in the first place? How do they get the materials there? How does it actually how does it grow? How does it get built? And how does it get disassembled?
Right.
How does it get unbuilt? So these are kind of key things that works in time as well, because if you skip one step, you're no longer able to get the material in the first place to get it built. Or maybe it's all happening offside and then float, it kind of travels there by the sea. I don't know. So it's just something kind of interesting. Sorry, not interesting, but it's something that it will be good to address, or suggest, So all time kind of related things.
We have proposed motorboats and other ways to reach the site, but yes. Thank you.
Yeah, thanks for the beautiful presentation. Project very well documented, very clear, and you studied very deeply the phenomena that are affecting the project. Also, the level of simulation you have been producing is quite impressive. I guess having this simulation of deposition and these waves. I was very impressed with this particle system simulating this waves effect. I think was very impressive. So, was impressive. So very well done. I think there are some aspects of the project that, since you've done so much, I think there are some aspects that could give further depth to the project. Let's say, for example, considering tidal effect, or let's say also the changing of the sea level over time, would be something to be probably addressed. And also, I think your project is quite different from the previous projects. While the previous project had been trying to face a problem and find a human solution to a problem, you are actually trying to interact with a natural phenomena that, at least from the presentation, not necessarily is a bad thing, but it's just natural evolution of a site, but that interact with a let's say human activity like the farming of the oysters, and somehow you find a sort of low-tech approach to how low-tech and high-tech in the way you simulate it, but you try to find a dialogue between what nature wants to do and what human needs to do to survive and to take advantage of the economy that historically was there. So I think it's different, very different and very complex from this point of view. I think so. This aspect needs to be highlighted because it's a unique characteristic of your approach to sustainability. I think this is an important thing because while your system is acting, to preserve this traditional economic activity there, there is something more it could do, because it could, for example, be deployed also to protect, for example, the coastline. So there are some other aspects that you could consider. So asking yourself, what's the long-term impact of oyster farming, for example, on the environment itself? So not looking only how the environment is changing, how it's going to affect the oyster farming, but how the oyster farming is affecting the environment itself, and how it could be affected if, for example, the salt level in the water is going to change in the future because of increased water level. So these kind of things are important because if you think about that, your system could do even more than what it's doing without changing much, I think. And another aspect, I think, is the architecture element that goes on top of the infrastructure that you're building for the oyster farming. These probably are a couple of comments that I would consider, at least I would try to explain, because this, one issue, when you have, imagine you're going to stay there, sell the oysters, or work on the oyster for a long time, you're going to have a lot of sun. So probably the way a shadow analysis or analyzing how the architecture you're designing is providing proper shades to this space would be kind of important to explain how you're going to give to these people a comfortable working environment, providing enough shades, and also how you're going to help people to walk across these. Maybe it looks 100-meter walk. Like imagine an old person that wants to go around, and in a warm day it may become tough for them to go around if they don't have proper shading. And another aspect that is curious is that I found very interesting simulation about how you create this closed system, these structural canopies that I think is very successful. But when it comes to these individual, let's say, shading system that have only one, is like a cantilevering system, so only one anchor point, I think you should be considering the impact of wind, because you're in the middle of the sea. There is not much protecting you. So you can have, let's say, for example, cold wind currents that come suddenly from the top. I mean, on the seaside probably no, but there is definitely wind is going to be an important factor, because you can have, strong wind flows that may, flip some of these elements, or may, it may be difficult for this vernacular structure to resist to this wind condition. So I think probably a closed system would be easier to justify. But it's just for your consideration. But I see that something that probably should be considered. But in general, very interesting. And I think when you talk about digital twins, to have a digital twins is not a digital replica of a physical asset. Is a system has a two-way communication. So you have a digital twin if you're able to gather data and if you're able to transfer data. So that's where you get a digital twin. So if you want to achieve a digital twin, probably will be interesting to have a bit more, develop a little bit more this diagram you have been developing. That's very nice, but where you really explain, the two ways of data flow. So, but in general, very interesting, and congratulations. Thank you.
Thank you.
Yes, thank you so much.
Thank you.
Okay, great. Thank you, everyone. And I just want to, on behalf of the faculty of EmTech, congratulate our students for their great projects. And please join me to thank our jury members here today with their insightful feedback. For those of you who are tuning online, we'll be back here at 6:30 p.m. with a keynote lecture from Wolf Mangeldorf, the Global Head of Innovation Technology from BR Happold. Thank you all, and have a good day.